Good morning, everyone. I am Prashant Kumar and presenting today with Abhinab and Deepraj. Together, we will walk you through the paper Neural Machine Translation by Jointly Learning to Align and Translate by Badhanu Chow Bengio, published at ICRL 2015. This paper introduced the attention mechanism, an idea so fundamental that it became the core of transformer architecture, BERT, GPT, and every large language model you have ever heard of today. Uh, Here's how the content is structured. We start with the problem, build upon the solution and the math, walk through the worked example, look at the result, and finish with long term legacy. Let's start with the problem. The standard approach before this paper was encoder decoder architecture. The diagram on this slide shows it. Source word feed into the RNN uh, encoder, which produce hidden state one by one. At the end of the statement, the very last hidden state become a single fixed vector. That orange circle labeled fixed vector C. This one vector is then handed to decoder, which generate the entire translation for it. Here is the critical limitation. The fixed size of the vector has to hold everything, every word, every grammatical relationship, every nuances of the source sentence, regardless whether the sentence is 50 word or 5 word. The vector doesn't grow with the input. Think of it like trying to summarize a full paragraph into a single sentence, then asking someone to reconstruct the whole paragraph from the summary alone. You are going to lose things. The consequences was already documented empirically. Blue score, our translation metrics, quantity metrics, drops sharply for sentence longer than 30 words. The model simply forgot early part from the long input. The bottleneck was not hypothesis, it was measured failure. So here is the fix. Instead of comprising everything into one vector upfront, keep all the encoder hidden state and let the decoder selectively query them at every step. Think how human translate actually works. You don't memorize the whole sentence and then translate from memory. You keep the original in front of you. When you need the word, a specific phrase, you glance back at the relevant part of the source. You, your attention is dynamically and selectively. This paper teaches the network to do so same. The mechanism has three steps. Step 1, encode. Run bidirectional RNN over the source to get one annotated vector H for every source word. Capture both left and the right context. Step 2, score. For each source position J, ask small feed forward network how relevant is this position. Give the decoder is about to generate. This give a energy score. And then the step 3, attend. Run softmax over the score to get attention weight alpha that sum to 1 across all source position. Then for the context vector C as their weight sum. Crucially, the context vector is recomputed fresh at every decoder step. The target word get its own custom view of the source. Let's look at the architecture. On the right, you can see the bidirectional encoder, the tail row of the forward RNN. Read the source from left to right, produce hidden state H1 through H4. The purple row, backward RNN, same input but read from right to left. Each position J, we concatenate the forward and backward state. That concatenated vector Hij lives in R raised to 2 power n, double the size of each individual hidden state, and that it carries the information about the full sentence, not just the prefix up to the word J. Now, the attention give the decoder previous hidden state Sij and each encoder attention Hij that aligned model compute an energy score, which you can see here. Softmax over the score give alpha. The context vector Cij is the weighted sum of all annotation. The decoder then updates its state Si minus 1, the previous word yi minus 1, and this new Ci. Everything encoder alignment model decoder is trained jointly from scratch. Now let's go through four step uh, precisely. Attention, mathematic of attention. Step 1, encode. Run the by RNN. If each RNN has 1000 hidden state, every annotation is 2000 dimension vector. Step 2, source score. The alignment model compute EIJ, which you can see here, and we are using 10H here. That doesn't depend on the decoder step I. You can uh, pre-compute it once all the source position before decode starts. Step 3, softmax to get weights. The weight sum to 1 over the all source position. You can interpret aij as the probability that target word I was translated from source word j. Step 4, compute context vector. CI, a weighted average of all annotation. Because this is smooth differential function, softmax followed by a weighted sum gradient from loss follow all the way through Ci, through Aij, through Eij back to Wa, Ua, and Va. The alignment is learned jointly, not separate training. So let's make this concrete. Here is the worked example. Source sentence is, you can see here, is translated into three different region. Watch what happen when the model generate each French word. When generating zone, you can see here it put 75% of its attention on the English word area. And similarly, if you move forward and uh, translating economic, it put 70% of the attention on the word economic. So the model has learned purely from example of English French sentence pair with no explicit grammar rule. That's this practical adjective noun reordering is the correct thing to do. No hard coding, linguistic knowledge, just learn AIJ weight. Now I would like to hand over the rest of the presentation to my co-presenter Abhinab.
Thank you, Prashant. Moving on to slide 8, we can actually see what the model is looking at. While it translates, this can be visualized by using the attention heat map for translating the English sentences into French. Here, we can see the x-axis is showing the English words and the y-axis is showing the French words. The brightness of each square represents the attention. The brighter the color means stronger the attention. If we look at the diagonal line, it shows that many words, the translation is just a monotonic word by word mapping. But here is where it gets smart. Look at the off diagonal bright spots. In English, we say August 1992, but the model easily handles the mapping. It also perfectly handles many to one mapping, like the word to was signed to eat. This effectively learns the grammar and word differences between the two languages all on its own. Now let's look at the experimental setup which was used by the authors to prove how the attention works. They trained their model on experimental setup. They trained their model on a dataset of 348 million words. They compared two main types of model: the standard baseline model with attention, without attention, called RNN-ENC, and their new attention-based model called RNN Search. They trained versions of both the model on sentences up to 30 words long and versions on sentences up to 50 words long. Finally, they compared the result against Moses, which was the absolute state of the art phrase based system at that time. They used the blue score to measure performance, where higher score means a better translation. So, now let's look at the results of this experiment. So, as you can see, the blue scores are very clear. The new model RNN search beats the RNN ENC in almost every comparison. For example, on sentences up to 50 words, RNN search only scored 26.75, whereas the RNN encoder RN RNN search scored 34, which is a massive jump of 9 points. Even more impressively, when they trained the attention model on longer sentences, that means longer than 50, it scored 36.15 on known words. This practically matched the state of the art Moses system, even though Moses had an unfair advantage as it was trained on a massive dataset of 418 million words that the neural network never saw. Now let's look at the graphs. The graphs is perhaps the most important visual in the whole representation. It plots the translation quality against the length of the sentence. Now let's look at the red line representing the standard model where without attention the performance drops after 30 words, 20-30 words, and the model simply forgets the beginning of the sentence. This Now let's look at the blue line. Uh, for RNN search attention models, the attention stays almost flat and stable. Even the sentences stretch beyond 50 to 60 words. This proves the author's main theory. The fixed length vector is in older model was severe bottleneck, and attention completely solved it. Now let's look at why the sentences are so robust and can handle so long sentences so well. There are four main reasons. No squashing. We no longer try to compress everything in a 50-word sentence into a single vector. The information is kept distributed across all the words. Local focus. At every step, the model only focuses heavily on 3 to 5 words that actually matter right now and ignore the rest. Then there is direct gradient path. The output is directly connected to the input or the source words, meaning the network learns much more easily without gradients vanishing over long sentences. And adaptable context. The model independently decides what it looks for in every single word it generates. Now let's do a qualitative analysis for the long sentence translation. To put this into perspective, let's look at a real world example translating a complex 40-word medical sentence. The old model starts off fine, but halfway through it literally forgets what it was talking about. It forgets the key phrases based on his status entirely and makes up an ending about health status. The attention model translates the entire sentence perfectly. Because it has attention, it does not have to memorize the whole sentence. When it gets to the end of the French translation, it looks back at the beginning of the English sentence to find the information it needs. Now let's look. It's worth noting why the authors use soft alignment instead of the old hard alignment. Hard alignment is binary. It maps one target word to exactly one sentence word, source word. That is A0 or A1. It struggles with translating phrases like the man into the single French word la home. And because it's hard mathematical step, you can't train a neural network through it easily. Soft alignment, which the paper introduces, uses continuous probability percentages. The model can spread its attention across multiple words at once. Crucially, because it uses smooth probabilities, the match is fully differentiable. This means the model learns how to translate and how to align words at the exact same time automatically using back propagation. So the legacy and impact. The impact of 2014 paper cannot be overstated. It is the foundation of modern AI. By 2016, Google used the exact attention mechanism to completely replace 10 years of old translation technology overnight in Google Translate. In 2017, researchers realized that if attention is so powerful, maybe we don't need the rest of the complex model. They published Attention is All You Need, creating a transformer architecture. This led to models like BERT and GPT in 2018, and eventually to the large language models we use today like ChatGPT, Claude, and Gemini. They are all built on the core idea: teach the model to attend to what matters. To wrap up, slide 16 shows how close Badhanau's 2014 model is to the famous 2017 transformer. The core concepts of query, a key, and a value exist in both. Bahdanau used an RNN hidden state and annotations to create scores, while transformer uses learnable linear projection. Ultimately, the transformer is essentially taking the Badhanau attention, making the match simpler and more parallel, using dot products and running multiple versions of it at the same time, which we all now know as multiple head attention. This is the root of all modern tech AI. Now I would like to uh, call Deepraj to present the code demos. Thank you.
Uh, thank you, Avinav. It was such a nice pleasure for us to have you to explain the slides in such a meaningful way. So, without wasting time, let me share my screen for the code demo. Just a minute. Avinav, you can share stop sharing your screen. So here it is. The thing is that we will be explaining the thing in terms of PyTorch implementation using the official some of the code that we have taken out from the official implementation, and also we try to present that thing from scratch. So we created this encoder, okay, and then in encoder we have declared the embeddings as well as the bidirectional RNNs, and then we have passed on the forward method, getting the embeddings and passing on it in the bidirectional RNN and getting the output and hidden dimensions. And again we have also created a cross attention an attention module where we have declared this Badhanu attention, and we get W, U, and V out of the linear embedding, out of the linear layers, and passing on the dimensions as per the requirement. And then we are obtaining the alpha and C value out of those WA, UA, and VA. And this is the entire attention, the encoder as well as the attention module. And a similar whole thing we have tried to do a live implementation of this thing on this collab module. You can go and have a hands-on on this, and we'll also be delivering the code demo in that stuff. Let me share that thing. Okay, so let me share that thing. Just a minute. So here is that collab notebook. If you guys want to have a hands-on demo, you can just go to that link and try this demo by yourself. So here is the same thing that we created the encoder out of the embedding and bidirectional level that we have just discussed before. So here is the decoder module. Here we are getting vocabulary, hidden dimension, as well as the attention module, and there we are trying to forward that forward that thing using the self embeddings as well as the RNN input. And then we are passing the prediction value, the S value, and alpha value. And this is our overall the evaluation function. Here we try to run the evaluation loss, and after that we get this demo. This is just a dummy data set that I've created. The more data that you have, the more better thing it will be for you. It's just for the demo purpose. If you want to have better results and if you have better computational power, you can just increase the data length or data set and do it on your own. And after that we have done numericalization. We also created a custom data set and data loader out of those data values, and then we created this collab function. And once that is done, we are creeping the batch size as 2, and then we are running this train data loader and validation data loader. Okay, so once that is done, we can see the thing. After that, we have created a sequence to sequence class where we just see whether this input data in English can be translated into French data. Okay, French sentence or the French data values. Okay, so for that we have also created this implementation. You can just run and see. And once that is done, we are again declaring this Badhanu attention module over here. And these are the hyperparameters where we kept input dimension, output dimension, encoder embedding dimension, decoder embedding dimension, hidden encoder dimension, and decoder hidden dimension. What are the things? We have declared it as per our convenience and as per our model that we have created, the architecture that we've created. We can also tweak these hyperparameters and see which works best for you and which works best for your translation. So once that is done, we're declaring the model, and then we're keeping a batch size of 64, SR source length and target length of 10 and 12 each. And then we're declaring the architecture. We can see over here it's exactly almost similar to the architecture that has been discussed in the paper. And once that is done, we are passing this thing again, and on CPU we are running it. And once that is done, we can see the training this what else the training function has also been created. Okay, where we create the training loss. And for this validation and training, we are looping it using now 5 epochs, but you can increase it to 100 or whatsoever upon your computational power and your data needs. So once you have run, we can see the training loss is decreasing, but validation loss is also increasing. This is because This can also be validated from these graph, because training loss is decreasing over time and validation loss is increasing because we are having such a small data set. If we had large number of data points in our data values in our data set, and if you could have done this for more large number of time, like more than at least like 50 to 100 epochs, you can eventually see this validation loss getting merged with this training loss, and both will come down eventually together and merge at the same minima, right? So that is the thing. So I think that is what our code presentation was. So let me stop sharing the screen and let me share back the file once again. I mean, the live demo. So that was the live demo. Okay. And so let me summarize entirely what we tried to explain this, how we try to explain this paper and what are the key takeaways from this paper. So first, we again discussed that this is a fixed length. In this, the key term fixed length, that is a bottleneck. Okay. And taking that thing, we also learned the attention is a dynamic context, is not a static context. And soft alignment is differential. The third key takeaway, that is soft alignment is differential, it is not non-differentiable, because alpha value can be determined within range of 0 and 1, and it is continuous, it is a series of continuous probabilities. And also like what we learn is like in the fourth key takeaway, it was like bidirectional RN, it captures the full context from beginning to end, it doesn't forget the stuff, unlike the previous RNN stuffs. And the fifth takeaway, and one of the most important key takeaway of this thing, was that it laid the foundation of modern LLP, right? Like how attention and how the attention that was proposed over here, it formed the foundation of modern LLP. And this paper laid the foundation for the revolutionary papers like transformers, BERTs, and all the modern LLMs and GPTs that we use today. Okay, so that was the quick run through, and these are the references that we have all used for explaining this slide. I mean, there are much more references, but these are the major references that we use for explaining the slide. And I think that is all. Thank you. Thank you, my all dear presentators over here, both Abhinav and Prashant, as well as Dr. Anand Mishra and his TS, for giving us this beautiful and beautiful and beautiful and good platform for explaining this entire paper. And we also got to learn a lot of things, and I think that is good a way for us to conclude this entire presentation. Thank you all.
Hello, my name is Mangalton Okram, and today I'll be presenting the start of the paper, Enriching Word Vectors with Subword Information. So it is basically the foundational, this introduce FastText, which is one of the most practically useful word embedding models ever built. So it directly solves a fundamental gap in how models like Word2Vec and Glove represent languages. Moving on to the next slide, we have our table of content. So we'll begin by identifying the core problem with classic word embeddings, then motivate why character level information matters. So we'll then revisit the skipgram model, understand negative sampling, and then dive deep into FastText subword model, like how it is built, trained, and evaluated. Finally, we'll look at like results across multiple languages and tasks. We will also run a live demo and summarize the key takeaways. So here we start with the problem with classical word embeddings, which we can say before we can appreciate what FastText does, we need to understand what's broken in Word2Vec and Glove. So let's start with the problem one, which is the auto vocabulary. So classic models like Word2Vec, they assign one fixed vector per word. So if a word was not seen during the training, say like gastroenterolosis in a general corpus, the model simply produces a zero vector. So it has absolutely no way to handle that word. This is a critical failure in real-world deployment. And now coming to problem two, we have rare word problem. So words that appear fewer than 5 times in training data, they get very poor vector representations. There simply isn't enough co-occurrence signal to learn a meaningful embedding. Like, for example, when we talk about medical jargon, legal terminology, and technical terms, they suffer heavily from this. And moving on to problem three, like we have morphological blindness.
So this is the deepest problem. Like consider, say, we have run, running, runs, and runner. So any native speaker, like English native speaker, they knows these are all related to the small same root concept, that is run. But what 2 does is it builds 4 completely independent vectors with no shared parameters between them. So like when we imagine finish, which can generate hundreds of valid word forms from a single root, word2vec would need to learn a separate vector for every single inflected form, which is incredibly inefficient and fails on like unseen forms, which the model has not been trained on. Moving on to the next slide, we have the real world motivation. So like languages such as Finnish, German, so they are morphologically complex. Like as we see from the table, it's like Finnish has 15 grammatical cases for nouns. Like just look at this table, like starting from the word telo, which means house, we have teloa, telosa, and so on. So these are all derived from the same root, but with different grammatical suffixes. But the further we go down the list, the less likely the word appeared in training data. So traditional models spread completely for these rare and out of vocabulary forms. This is not a corner case, like Finnish, Hungarian, Turkish, and many other languages are like this. Now, German compound words, like German can combine words into compound nouns. Like this tennis literally means table tennis, composed of like this, which means table, and tennis. So like word2vec would treat this tennis and tennis as entirely unrelated words. But FastText, on the other hand, will naturally detect that they share the tennis subpart. Right. So the FastText insight is that instead of assigning one vector to the whole word, it represents words through the set character n-grams. So this way, like telo share common n-grams with telostomachin, which I can't pronounce it correctly, and the representations are linked. Right. Even if the full long form was never seen in training, it can give some vector. It can generalize well for that vector. For that word, giving a vector, which is the sum of their corresponding n-grams. Moving on to the next slide, let's like have a quick review of what skipgram was. So FastText is built on top of the skipgram model. So we need to make sure the audience, in skipgram, what it does is, given a sentence like the cat sat on the mat and a target word like set with a context word of window size of let's say 2, the context words are cat on the left and on the right. So the skipgram model tries to learn word vector such that the target word can predict these context words well. But the main intuition is, if words frequently appear near each other, so their vectors should be close in a vector space. So words that almost never appear together should have vectors that are really far apart. Right. So we have our objective function here. So what the model is trying to do is it will try to maximize the sum over all position t's and their context words are C here of the log probability of seeing context word WC given target WT. So the formula shown is sum over t equal to 1 to t, sum over C in CT of log WC given WT, which is like given the context, given the target word, what is the context? So this is essentially saying across the whole corpus, so for each word and its context, let's just maximize the probability of predicting the right context words, right? So like the diagram, right side of the slide, it shows that the neural network architecture of the skipgram model. So the first initial input is a one whole vector representation, which is a target word, WT. So it passes through a single hidden layer, no activation, just a weight matrix W of size, let's say the V cross N, where V is the vocabulary size and N is the embedding dimension, right? So the output layer is another weight matrix W dash of size N cross V. So producing scores for each word in the vocabulary. So after softmax, we get probabilities. The model is trained to maximize the probability of context words appearing around a specific target word. right? So think of the hidden layer representation as the word vector. This is what we extract and use downstream after training. Yeah. So like moving on to the next slide, let's refresh our negative sampling as well. So now we address like a key practical problem, right? The skipgram objective as defined requires a softmax over the entire vocabulary. So let's say if the vocabulary has 300,000 words, the denominator of the softmax here like requires 300,000 exponentials at every training step. So that is computationally like really prohibitive, right? So coming to the solution of this, instead of using softmax, we use a binary classification. So instead of asking like which word is the context word among all W words in the vocabulary, so we ask just a simpler question like did word X actually appear near word Y in the corpus? So the answer can be yes or no, right? So this turns a multi-class softmax problem into a set of independent binary classification tasks. So like we are supposed to have yes or no. So what we're going to do is we will create positive pairs. Like for target word, like in the uh, sentence here, that for the target word brown in the sentence, the quick brown fox jumps, right? So with a window size of 2, the context words are quick, fox, the, and jumps. So we create positive training parts, pairs like brown, quick, brown fox, brown the, brown jumps. So these are the real co-occurrences, right? Which are the ground truth. They are treated as positives. Not from the softmax formula on this slide key, probability of WT given the WC given WT, which is the like e to the power score of WT and WC divided by sum of this entire vocabulary given to the power e to the power the score of WT and J. So the scoring function as WT and WC is as a dot product of the input vector UWT and output vector YWC. So the denominator sums like over all words Z in the vocabulary, and that is the really expensive part, right? So moving on to the next negative sampling, here we have the loss function as well. So like on step 2, what we're going to do is we will generate negative pairs. First, we have already generated positive pairs. Now we're going to generate negative pairs. So for each positive pair, we generate k negative pairs. So we can take k as a 5. So negative words are sampled randomly from the vocabulary using a special distribution where the probability of sampling a word is like proportional to its frequency raised to the power of 3 divided by 4. So 3 by 4 exponent is empirically found to work best. Like it balances between purely uniform sampling and frequency proportional sampling. So for positive pair, let's say we have positive pair brown quick. The 5 negative pairs might be brown apple, which are just randomly chosen, right? So brown apple, brown car, brown run, brown algorithm. So the model needs to learn that brown goes with quick and give the high score, but not with apple, and it will give the low score. So step 3, may we have loss function. So the loss for one target word, context word pair plus k negative is log of 1 plus e to the power minus score of WT comma WC plus summation of sum over negatives, right? So for all the negative pairs, log of 1 plus the e to the power score of WT and like then the negative random pair. So like the first log, it will solve the like the positive one, and the summation one, it will solve. It will like look for the loss function. It will calculate the loss function for the negative pairs. Uh, Negative, yeah. So for negatives, we want the score to be low, so the second term is small, And for the positive pair, we want the score as WT, WC, which is actually the dot product of WT and WC. I mean, the vector representation of WT and WC, which is UT and VC, right? So to be high, so that the first term is small. And for negative, we want the score to be low so that the second term is small. The full objective sums this overall position C in the corpus, like all context position C, and their associated negatives, like some C in CT, given like S the WT WC plus sum of N in NTC, where this is a negative pairs one, where L of x is equal to log of 1 plus e to the power minus x. It is the logistic loss. Yeah, and like when we move on to the next step, we have backpropagation for negative sampling. So like we can see there is gradient update. So like we have seen how we calculate loss in the previous slide. So after computing the loss, so we calculate the gradient with respect to every parameter in the model, like specifically the input vector, like v round for the target word, and the context vector u quick, u fox, etc. for each positive and negative context word. So we can use stochastic gradient descent. So SCD10 updates each factor by taking a small step in the direction that actually decreases the loss. The learning rate determines the step size and is linearly decayed throughout training. Right, and here the key intuition is for positive samples, if the model predicts like quick and brown, like if the model predicts brown and quick should not appear together. So low score when they should be high. The gradient pushes their vectors closer together. And for negative samples, like if the model predicts brown and apple should appear together, like high score when they shouldn't. So the gradient pushes their vectors like farther apart. Like since they are the negative samples. So this is why word-to-vec embeddings end up encoding semantic similarity. So words that appear in similar contexts get pushed to similar regions of the vector space through thousands of these gradient updates. But the important implementation detail is training is parallelized using Hopwell. So all CPU threads share the same parameter vectors and update them asynchronously, so without logs. So this works surprisingly well in practice because the gradient updates are sparse. So only the vector of the words in the current context window are updated. So like let's move on to the next slide, which actually so how FastText work. A FastText key upgrade only standard skip gram is this. Instead of learning one vector per word, we represent each word as a bag of character n-grams. And we can compute the word vector as the sum of those n-gram vectors. So here we can see the step-by-step example with where with the word where and n equal to 3, right, the n-gram tree. So like step one, maybe we can see like add boundary markers. So why do we need this? To wrap the word in angle brackets, this marks the start and end of the word, right? So these are special characters which are not used in regular text. And in the second step, like we extract all 3 grams from the bracketed form, like WH, like the first bracket and then WH, where the WIC, ICR, ERE, RE, and the N notation. So notice the full word where is also is also added as a special token to allow the model to still have the whole word representation. So it is actually added along with the corresponding n-grams. In step 3, the word vector we can calculate as the sum of all n-gram vectors, like sum over G in GW of like G is the like whole like n-gram vectors of ZG, which is the vector for the for the n-gram word, and VC, which is the context vector. So where GW is the set of all n-gram in word W, and ZG is the vector for n-gram G, and VC is the output context vector, right? So why boundary markers matter is the marker distinguishes a prefix, right? So it signals it starts with WH from an interior n-gram, and the n marker marks suffixes. For example, let's take it the n-gram her from inside the word where is different from the actual word her, like it denotes female. So so it makes it different from the like from the actual word and the corresponding uh, engram. So this is crucial for morphological capture, and we are summing the vectors because like the vectors are summed because each engram contributes independently to the meaning, and the sum is cheap to compute and works surprisingly well. So it's equivalent to treating the word as an unordered vec of subpieces. And like let's move on to the next slide. So like now we have a new problem. The vocabulary of possible character engrams is really huge. When we talk about English language, for English with n ranging from 3 to 6 characters, and considering all possible character sequences, we could easily end up with millions of distinct engrams, right? So storing a separate vector for ease would require enormous memory. And what is the solution here? The paper have introduced a new trick called the hashing trick. So instead of maintaining a full dictionary of all n-grams, we map each n-gram to an integer index in a fixed range from 1 to k, right? So using a hash function. The paper uses the FNV 1A, that is Fowler Nolvo hash function, which is a non-cryptographic hash function known for its speed and good distribution properties. So in the paper, k is set to 2 million. This means that the model learns exactly 2 million n-gram vectors regarding of how many distinct n-grams exist in the corpus. So here on the right side, we have the example flow. So the word where after the bracket has been encoded, like extract n-grams. Like here we can see there is the five n-grams, and then hash is to an index. Like every one of them, they're hashed into an index. Like said for WHC we have 1023, and WHC we have 88231. So these are the hash index, right? So when we look up those five vectors, we can get their vectors, vector representation. So if we sum them up, we get the vector for the particular word where, right? And the problem is that collision may happen. So two different n-grams might hash to the same bucket, but since it is 2 million, what is it? 2 million hashing. So this is acceptable. So in practice, the model is robust to a small collision rate, but the benefit of constant memory uses outweighs the minor noise that is happening from collisions. From the next slide, my co-presenter, Deepraj Majumdar, will continue.
Thank you, Mangalton. So you can stop sharing your screen. Let me share my screen. So I'll be sharing my screen. Okay, just a minute. So yeah, so myself Deepraj Majumdar. So and I'll be continuing the rest of the other content of the slide. Here we'll be having a hands-on code example. This slide actually shows Python code for extracting n-grams, which is the foundation of how FastText works internally. The function get n-grams, okay, which is having three this parameters that are word and min and max. Okay, this first traps the word in boundary markers word, then it literally iterates over all n from n min to n max and all string positions I, extracting every window of size n. The result is the list of the character engrams for word where, inverted quotes, the output will be like as we all can see, wh whe HERERE. And we have also seen the example that Mangalton gave. Okay, it's somewhat similar to that only. So notice how the boundary markers appears the short over the shorter n-grams, right? Like underground, that is beginning, okay, that is less than sign, then w, then h. Okay, this captures the word start, and also it ends like with re and you know greater than sign, where it captures the word end. So three key insights from this, from the boxes on the right side of the slide. Why boundary markers matter? Because as we all know that where it helps detecting words starting with W, R, E, and mark, and it also helps detecting words that ends in with RE. Importantly, they distinguish the engrams HER from inside the word WHERE, where versus the standalone word HER, which would be encoded as H beginning, like in the starting HER and ending. So that is the point. Like why some vectors? Because each engram contributes the learned meaning. That is, rare word still gets reasonable vectors because they share n-grams with common words. For example, a rare medical term where sharing n-grams with more common medical words that happened in training, right? So for also the UOV exam handling, that is also an important thing. Even the word like there are like pneumo ultra microscopic, which would never appear in training data, right? So can it be represented by summing vectors of engrams like pneumon, then scopic, etc., which may be appeared in other medical words, right? This is the fundamental advantage over word to vec. And in the next slide, I'll say, in the next slide, this slide where we are also discussing about the training setup and hyperparameters, it actually describes what are the trained and how. Like understanding the experimental setup is essential for interpreting the results. Like the training data, the models were trained on Wikipedia data dumps in 9 languages that includes Arabic, Czech, German, English, Spanish, okay, English, Spanish, and also just a minute. English, Spanish, and also like other words. For example, Arabic and Russian, Romanian, okay, Italian, and also the other words like French and and like I'll say Czech. Okay, so these languages were chosen because they cover a wide range of morphological complexity, from relatively simple English to highly inflected ones like the Czech, Russian, and Finnish like. And also the Harper parameters, these are generally including vector dimensions of 300. Each words have with by having the engrams that gets a 300 dimensional vectors, and this is the standard in the field. Like for example, the negative samples, they were 5 per positive pair. Context window, which had randomly sampled between 1 and 5 for each training example. And we also kept they also kept like the minimum word frequency of 5, which appears fewer than 5 times and are removed from the vocabulary if they're simply too large or too learned. And n-gram range, we also kept that thing from 3 to 6. Not we, the authors. And those characters includes both inclusive ones and the exclusive ones. And also the learning rate was 0.05 for FastText and 0.025 for skip gram baselines. So different because they have different objective scales anyway. And hash bucket size was kept as 2 million. And models that they also compared include the baseline models like skipgram, word2vec, cbow, continuous bag of words, and skipgram without UOV handling, and also the skipgram with UOV words, getting them as null vectors. Okay, and they also included SISG sub info skipgram with UOV handling, and UOV words get vectors from their engrams. Okay, and this comparison between SSIG and SSIG UOV isolates the benefit of UOV engram representations. Apart from that, the speed FastText processes, it includes like 105,000 words, and second thread compared to 145,000 that were used for the skipgram baselines. This means FastText is almost like 1.5 times slower, right? Despite learning much richer character level representations. And this is also the this was also the key practical advantage. So in the next slide, this generally includes the scratch pytorch implementation of FastText, which is excellent for building intuition. And we also build our intuition going through this code. So workaround, this file includes like it included subwords.py, where this is the same function from side 11, but it is shown in context over here. It takes a word, adds boundary markers, and extracts all ngram from nmin to nmax. And then there was this fasttext.py, this is the core model The model has two embedding layers: n-gram embedding and embedding matrix of size n-gram size into dimension. This stores one vector for each of the 2 million n-gram hash buckets. Context embedding, the embedding matrix of size vocabulary size cross dimension. This stores the output context vectors for each word in the vocabulary. After that, we do a forward pass here, given a list of n-gram indices from like a word derived from hashing. Looking up each n-gram embedding vector, the result z has shape of like n-grams and dimension, as you can see here in the code. The some I mean some summing across those n number of n-gram dimensions to get one word vec for dimension dim, as we can see here in this code section, right? And there was also this training loss, that can be used, was this logarithmic sigmoid loss. And this function is having this training objective there, where you pass the sigmoid of score of this position of the negative as well as the positive, and then we take the sum of both the sum of all this dimension across the logarithmic size of this entire log function of the negative score, while we add it with the only logarithmic value of the score sigmoid of the score position. So that was the thing. And this is exactly the negative sampling objective, as we can see from slide 7 that Mangalton explained earlier. And now we explained in one line the this thing, actually the gradient flows back through the summation to the update of n-gram vectors equally, right? So that is the key insight, like the gradient update propagates through the summation. So in every n-gram in the world receives the same gradient signal. This means that if micromanaging and micromanage share the n-gram micro, both training examples update the shared n-gram vector, effectively giving it almost like the 2 times training signal, right? So in the next slide, this is actually the full training objective, step by step, as we'll explain. This slide formalizes actually the training objective and walks through a concrete example. Let's walk through it carefully. So the first one is the part A, where there's a formal objective. The loss for one word W and context C pair, that is LWC, is a logarithmic sigma, where we take S of WC plus sum of T minus Pn, and logarithmic of sigma negative SWT, where sigma is the sigmoid function converting scores to probability between 0 and 1, and W comma C is the similarity score to probability between 0 and 1. And this is also between the word and the context, the dot product of the summed n-gram vectors and the context vector P. And Pn is the noise distribution used for negative sampling, and T minus Pn, which means negative words T sampled from that distribution. And next, part B, the worked example: sentence, the cat sat on the mat, target word sat, okay, and context word cat. So step 1, we need to extract n-grams, add boundaries to get sat, okay, since it's the target word. And with word token sat, so g sat is equal to sa beginning of sa, then sat and at end of that thing, and again beginning and then sat and then ending, okay. So in step 2, we build the word vector. That is, the word vector for sat is the sum of the 4 n-gram vectors, that is u sat is equal to z sat beginning plus z sat plus z of at ending, right, plus z of entire beginning sat at and then ending. So each z is a 3-dimensional vector that is learned during training. This is very small example, since sat is only 3 letter. Longer words like micromanaging would have many more n-grams and a nicer representation. Anyways, so the full training objective that we go will be by a step-by-step walkthrough. So in the step 3, continuing the word example from previous slide, in step 3, we scored the true context, that is computing s of sat cat, that is u sat dot vector of v cat. This is the dot product of the word for sat is sum of n-gram vectors with the context vector of cat. The training objective pushes this score to be high, meaning sat and cat uh, should have large dot product because they appear near each word in the corpus, right? So in step 4, we also go through sample negative words, like sample 5, which random words from the vocabulary that are not the actual context words, we can say. In this example, like the dog, the rain, blue sky, compute s sat noise, that is equal to u sat dot vector of noise for each of this. The training objective pushes these scores to be low, right? Meaning sat should not be predicted from these random modes. Okay, I hope you all are going along with that thing. Anyways, so going on to step 5, we see a gradient update. The gradient of the loss with respect to each engram gz is delta L by delta Zg, that is sigma of S minus 1 into Vc for all the G in capital, I mean in GW, right? So notice that the key property of all n-gram in this word receive the same gradient. There's no differentiation between n-gram which was responsible. They all get updated equally. So this equal update rule is what belongs sharing of morphological information. The n-gram that is at ending appears at sat, cat, bat, hat, rat, uh, every time any of these words is trained on, right? So that shared n-gram vector gets updated, and by the end of training, I mean end of training, the add vector ending at vector encodes the semantic and syntactic meaning associated with at endings, right? So that is the thing. So moving on to slide 16, we can see the word similarity tasks over here, and this result shows that first task is word similarity, comparing the model similarity scores, that is cosine similarity between word vectors against human judgments. How it is evaluated, it is the thing is that using space marks rank correlation coefficients between human assigned similarity scores and the model's cosine similarity scores. A higher value means the model's ranking of word pairs by similarity match uh, human intuitions better, right? So the again we see the bar chart. This shows result across 10 datasets spanning multiple languages. Blue equal to SG, that is Cape Gram. Orange is equal to CBOW, and green is the missing FastText without OOF handling, and red is SSIG fastest with OOF handling. The red bars are what we care about most, and the key findings are that fast text, okay, that is SSIG and red, it wins on 6 out of 7 data sets. The only exception is English WS353 data. We'll explain that why in a moment. And biggest gain for German and Russian, plus 9 points on German and plus 7 on Russian, compared to the skip gram uh, baseline. These are morphologically rich languages which many words forms compound words like German and case infections like Russians. This is exactly where subboard information helps the most. And point number 3 that we need to note, like why English WS353 performs, similarly. English S353 contains common frequent words for which word2vec already learns good vectors. When word appears thousands of times in training data, the standard approach works fine. You don't need to sub give them the sub or trick or whatsoever. But fastest advantage is most pronounced for rare and morphological complex words. Another thing is, like, there is also an OOF advantage, as we have discussed before, like common SSIG word that we can see here over green null vectors for OOF, and versus the SSIG that is red n-gram vectors for OOF. SSIG is constantly equal for or better even, proving that the n-gram approach produces meaningful representation even for words that we have never seen in training. So next slide, we see slide 17. Here's the analogy task, word analogy task. The word analogy task is a different capability where reasoning about relationship between words. The classic example is Paris to France as Berlin is to Germany. Obviously, we can all say that this is solved by vector arithmetic, like vector Germany equal to vector Berlin minus vector France plus vector Paris. So two types of analogies, like syntactic test morphological relationship like run, running, walk, walking, semantic test, conceptual relationship like Paris, France, Berlin, Germany. The chart, I mean the left chart is equal to syntactic analogy, there's accuracy right, semantic analogy, there's accuracy languages shown. So Czech, German, English, Italian, blue SG, then we also see the color orange, CBOW, semantic green, FastTech. So these are the syntactic analogies, I mean the left chart. Here FastTech, it takes it generally the green one, it dominates across all languages. For Czech, it improves almost to like 52% to 78%, a massive plus 26% gain. This makes intuitive sense. Czech is highly inflected, and morphological patterns like verb conjugations are captured perfectly by shared characters in gram. We also see a semantic analogies right chart, where the FastText performs roughly on par with baseline for German and Italian. It's actually simply lower. This is because semantic relationships, capitals, countries don't benefit from character level information. Paris and France don't share, characters. The subword trick is less helpful here and can even, add noise. So here in the bottom line, FastText is better than Word2Vec for syntax heavy tasks, equivalent in morphological rich language, and roughly equivalent for semantic heavy tasks, right? So in the next slide, that is results, that is language modeling, LSTM plus FastText. This experiment tests whether FastText words like vectors serve as better initialization for downstream tasks, especially an LSTM based language model. So the setup, a recurrent neural network with 650 LSTM units is trained on language modeling, right? Predicting the next word. The models embedding layer which maps words to vectors. It is generally initialized with pre-trained word vectors. Lower perplexity is equal to better model, as we all know. The table here, the rows equals to method columns, and columns is equal to languages, that is Czech, CS Czech, D German, uh, I'm sorry, ES Spanish, FR French, and RU is equal to Russian. So lowering numbers are better. CLBL and CAN LM are state of the art baselines from other papers. LSTM, that is not pre-trained. Raw LSTM without any pre-trained embeddings. LSTM plus SG pre-trained with standard skipgram. LSTM plus fast text. SSIG is equal to pre-trained with our subword vectors. That is the highlighted green row. So result, as we can see, fast text, that initialization gives the better perplexity on all five languages. The improved varieties, that gives almost 8% of Czech versus skipgram, 13% for Russian, and 3% for Spanish, 2% for French. The biggest improvements are the most morphological complex improvement, or the languages that we see in Czech and Russian, Slavic languages. Smaller improvements for Romance languages like French and Spanish, which have simpler morphology. So the significance is that these improvements carry over from word representation to downstream tasks performance. FastText doesn't just learn better isolated word vectors; it actually helps the final model generalization better. So for Czech, with almost like 46,000 vocabulary, the gains are pronounced, right? So what we see, the remarkable finding works on smaller data. This is the perhaps most practical important result in the paper. The experiment trained models on increasing large fraction Wikipedia like 1%, 2%, 5%, 10%, 20%, 50%, and 100%, and evaluate performance. The two charts show result on German GUR 350 left and English RW right. So the stunning result, we will read this thing carefully because fast text, as we see, trained on just 5% of the data achieves better performance compared to on 66 specimen rank. Then CBAO, the blue one, trained on like 100% of the data, 62. On the English one, that is the right one, using just 1% of the Wikipedia fast text, it almost achieves a correlation of 45, better than CBAO 43 on the full data set. Why does this happen? Because Word2Vec needs to see each specific word from many times to learn a good vector for it, right? If telostaminakin, a word which appears only twice in the corpus, it gets a poor vector regarding of how much other data you have. Fast text, on the other hand, it appears in the word. The n-gram vectors are updated by all the more common words that share the substring. So even with small data, the vectors for rare and unseen words are bootstrapped from the n-grams they contain. So what is its practical implication? So what I'll say is, its practical implication, this means that this matters enormously for low resource NLP situations where you are training on specialized corpus like medical records, legal documents, code, etc., that might only have 10 of thousands of documents. Fastest will still produce useful representation where Word2Vec could fail, right? So what is the observation about saturation here? So here we see FastText performance saturates early. Adding more data beyond 20% doesn't help because it's already extracting all the morphological signal available. Whereas CBAO, it keeps improving slowly with more data. So in this last slide, not in the last slide, I mean in just few of the slides before the last one, we see that numbers, they tell us performance, right? we see the qualitative analysis. Here the number tell us the performance, but qualitative analysis also tells us what the model actually learned, right? So this slide has two parts: the nearest neighbor table. For rare and technical complex English word, we compare the nearest neighbors found by FastText. Okay, we also compare the nearest neighbors found by FastText versus standard skipgram by cosine similarity, like words like tilling. Okay, so FastText finds tile floor correct, right? Skipgram finds bookcases built-ins which are wrong. So if it found statistically co-occurring furniture words instead of morphological related words. So micromanaging, FastText finds micromanaged perfect morphological variants. Skipgram finds defang intensive, completely wrong. This just happened to appear in small similar context in the training data. So also there is like dendritic, which FastText finds dendrites correct. This shares the dendrit, that is the root. Skipgram finds epithelial P53 statistically co-occurrence from biology texts, but no morphological connections. Also, eateries, FastText finds restaurants, eatery good. Skipgram finds restaurants, delis, also reasonable, but not find it doesn't find the morphological variant eatery. So the key observation about engrams and morphologies: the author analyzed, which engram are most important for a word meaning, which engram, when removed from the word's representation, causes biggest change in the word vector. For example, German Auftragger, car driver. Most important engrams are Otto and Fahrer, the two more morphemes. For English, kindness, most important engrams are ness and kind. Unlucky, un and icky. Okay, siki, what I'll say, whatever. For French, verb forms like finiris, most important engrams are es, past conditional suffix, and fini, that is the root. So this shows that model implicitly learns morphological structure without any explicit linguistic supervision. No morphemes dictionary, no part of speech tracker, or no language specific rules were used in the training. So here is the live demo. If you all can see it, here we'll be doing a live demo. So let me share that screen anyways. I hope Mangalton is with me, right? Yeah, Mangalton just with this there. So thank you everyone for holding this patient, being patient and holding this much amount of patience. Can see, as we can see here, this is the live demo. So first is the installation and imports. As we all can see, we just need to do this installation or the few of the required stuff. Then these are the basic imports. Okay. So in section 2, we deal with ngram extraction, that is the heart of FastText. We will declare this function which we have discussed earlier, the same thing. And then we are doing this ngram extraction demo, where we use these shared engrams. Okay, word 1, word 2, and then n minimum and n max. I think we have already discussed all these things before. It's just the code representation of all these things. Just we have the things that I've explained before. Then for OOV words, the same thing. We are getting the total engram extracted, medically meaningful subparts, and then we're printing this sub. Like for example, this mono ultra microscopic word. Okay. Then in section 3, we are just converting word to vec and also checking like with the FastText the OOV problem live. These are corpus. Actually, it's not that big, it's small, but if you make it large, you can see even better results. Okay, these are just for the test stuff. You can run this code, okay, with our demo, and you can just check it once again on your own. We are just explaining the content so that it will be easier for you to have this demo done. Okay, so once that is done, then this critical OOF test, we do it over here, and we can see that the micromanaged word to vec response key error, but fastest it gets a valid vector, right? So it's obviously better. So in the last section 4, we are doing a training visualization and watching the vectors that we learn. So we do PCA, then we mark the stuff over there, and then we run all these tests over there, and we're saving it over the visualization like word to vec, skipgram, and FastText subboard. So just notice here how FastText clusters are morphological related words and are much more tightly aligned than word to vec, right? So this is the stuff over here. So in OOF handling, so in OOF handling, we can see over there that multiple word tests, like everything is working better. So we also see the stuff over there, and we also see the stuff over there, and we can also see how visualization OOF quality vector works. Okay, And we also marked and plotted this thing over there, and we get that gastroenterology, this kind of medically careful words, rerunning, unimaginable, kindly runners, micromanaged, all these things work over there in FastText OOF vector norms. Okay, then we get this section 6, that is morphological awareness, and we see the direct summary comparison over there for word to vec, ft sim, w to vec similarity, and ft wins, right? Then in section 7 we go through rare word nearest neighbors, and we get all these query and nearest neighbor words we can run and see. It's very easy. After that, we also visualize the nearest neighbors, and it works. We are getting from a range of 0.99 to 1. And then there is this section called vector arithmetic analogy task that we also do, and we get vector arithmetic from A to B, B to C, as C to what, that is man to king, and woman to what to vec is addressed, FTS is kingdom, but the expected thing should be queen. So in this manner, you can check and get whatever the things we get over there, and ultimately we get a general, like this vector arithmetic in geometrical visualization, how they're related and stuff. Then we get a multilingual demo in Hindi. Okay, and in section 10 we get fix. We also train it on Facebook's pre-trained fast text vectors. It's optional, but it requires downloading. If you download it, you can run it. And then this summary dashboard to get everything at once. So this is the summary dashboard. You can easily see, run, and have a look. Okay, and we see the n-gram count per word, cosine similarity, their character n-gram overlapping matrix, and also the OOF word vector names. So the final takeaways that we see, and these are these n-gram decomposition, OOF handling, morphological awareness, data efficiency, and legacy. Okay, so these are the code texts we can see. I think we are good to go with all these things, and if you guys really want, we have this link. You can go and try it on your own and check it how this code works, and go through a good hands-on over there. So let me get back to the slides. uh, before we conclude, let's finish this thing up. So that was the live demo. So these are the key takeaways. We see here how the n-gram representation works. And the second point was that, how word vector was the sum of n-gram vectors, right? And in 3 also we get to see how morphological rich languages works and improve. In then the fourth takeaway was how it improves syntactic tasks. And the fifth takeaway was how the pioneer of modern LLP foundation was done, right? So these are the takeaways. Because many word, as we can see over here, many word formations follow rules. It is possible to improve vector representation for morphological rich languages by using character level information, right? So I think that is it, and these are the references. So I would again, once again, like to thank Dr. Anand Mishra and respected TAs and respected Dr. Anand Mishra for giving us this beautiful platform, for representing this beautiful paper and presenting this in such an intuitive form. I hope this will help all of you to understand the paper and help you all to even go through and try coding on your own by using a live demo. In case if you face anything or any problem, you can always reach us. You can always reach Mangalton and reach me. And in that way, we'd like to conclude this presentation. Thanks everyone, and thanks Mangalton once again for being with me and presenting this slide. Thank you.
Hi, I am Arjun. Sarita and I will walk you through this seminal paper in this video presentation. Welcome everyone. This is based on a classic 1994 paper by Bernard Marialdo titled Tagging English Text with a Probabilistic Model, published in Computational Linguistics. Over the next roughly 20 minutes or so, we are going to cover 6 things: what POS tagging actually is and why it is hard, how to frame it as a mathematical problem, a specific probabilistic model called the tri-class HMM, 2 very different ways to train that model, the experiment results, including one that will probably surprise you, and finally, what all of this means for modern NLP. So let's get started. Here is the roadmap for today. We start with the basics. What is POS tagging and why does ambiguity make it hard? Then we formalize the problem mathematically, which gives us 2 different criteria for what the best answer even means. From there, we build the model, the tri-class HMM, and then we look at how it is structured. We then spend a good amount of time on training because that is where the interesting action happens in this paper. We look at the experimental results and unpack the main finding. And we close with takeaways and how this 1994 work connects to things you encounter today. Keep this roadmap in mind. We will come back to it mentally as we move through these sections. Our first section asks a very simple question: what is part of speech tagging and why should we care? Part of speech tagging is a task of assigning each word in a sentence its grammatical category. It's part of speech in context. Look at the example on this slide. We have the sentence, the cat sat on the mat. A POS tagger looks at each word and decides, is this a determiner or a noun or a verb or a preposition? And it does this for every single word. So the gets tagged determiner, sorry, DT for determiner, cat gets NN for noun, sat gets VBD for past tense verb, on gets IN for preposition, and so on. Now the paper we are studying used a reduced tag set of 76 tags, taken from the original 159 tags in the Lancaster tree bank. This still sounds like a lot, but it is a manageable inventory. Why does any of this matter? Well, POS tags are a foundation. Every downstream NLP task, whether it's parsing a sentence structure, translating between languages, or extracting information from text, or even synthesizing speech with the right intonation, benefits from knowing the grammatical role of each word. Get the tags right, and everything downstream gets easier. Get them wrong, and error cascades. The core challenge is lexical ambiguity. Here is the problem. Many words in English, especially the most common ones, can carry more than one POS tag depending on the context. And the context is everything. Take the word bank. In I went to the bank, it is clearly a noun of financial institutions. In the sentence, I bank with HSBC, it is a verb, the act of banking. And in the sentence, the river bank flooded, it is a noun again. But now, meaning the edge, but not the meaning the edge of a river. Three different uses, all valid, all requiring the tagger to look at surrounding context to decide correctly. Or take can, the word can, in she can swim. It is a modal verb. It expresses ability, right? In the sentence, open the can, however, it is a noun, a tin container, right? In the sentence, can the proposal, it is a verb meaning to cancel or discard. Same spelling, completely different grammatical roles. This ambiguity is what makes POS tagging non-trivial. You cannot just look up a word in a dictionary and get its tag. You have to resolve the ambiguity using context. This is precisely what probabilistic models are designed to do. Probabilistic formulation. Now that we know what the problem is, let us formalize it mathematically. This section introduces the notation and the two key criteria for solving it. Before we can write any equations, we need to agree on symbols. Let me walk through each one carefully. Capital W is a sentence of n words, written as W1, W2, all the way to Wn. So for the sentence, the cat sat, W would be, as seen in the example below, you have the cat sat, and n would be 3 here, right? All the 3 words you can see at the bottom of the slide. Capital T is a tag sentence of exactly the same length, that is T1, T2, T3 over here in this case. For our sentence, T might be, in this case, could be determiner DT, comma, noun, NN, comma, verb, VBD. The pair W, comma, T together is called an alignment. A sentence paired with a specific set of tag assignments. P, W, comma, T is the joint probability of that alignment. This number tells us how likely it is that this particular sentence appeared with this particular tags together. The higher the number, the more the model believes these tags fit these words. Finally, phi is a tagging procedure. It is a function that takes a sentence W and outputs a tag sentence T. Our job is to design the best possible phi. At the bottom of the slide is a concrete example to ground all this. W equals, as you can see in the brackets, the cat sat. T equals dt nn vbd, symbolizing determiner, noun, and verb. And together they form one alignment. Simple enough, right? But this notation scales to the full mathematical machinery we need. Two optimal tagging criteria. Now here is something subtle that most treatments gloss over. There are two mathematically distinct answers to the question, what is the best tag sequence? And they are not the same thing. The first is Viterbi tagging. Here we ask what single tag sequence T maximizes the probability of the entire sentence at once. The formula is phi of W equals argmax over T of P, bracket T given P. This is a sentence level optimization. We want the single most coherent mathematical reading of the whole sentence. It is implemented using dynamic programming, the Viterbi algorithm, and runs in big O of n times nt squared time, which is efficient. It is simpler to implement. It is linguistically interpretable and gives you a single consistent parts. The second one is maximum likelihood word level tagging. Here we ask a different question. For each position I, what is the most probable tag for just that word? Taking into account all possible ways the rest of the sentence could be tagged. The formula marginalizes over all tag sequences where position I has tag T. This is theoretically the correct criteria if your evaluation metric is per word accuracy. But it is more complex and crucially can produce tag sequences that are linguistically inconsistent because each word is optimized independently. Now, which should we use? Here is the paper's finding. Shown at the bottom of this slide in green, in practice, both methods produce almost identical results. They differ on fewer than 20 words out of 45,583 tested. So Viterbi wins on practical grounds. Same accuracy, which much simpler. This is our first hint that theoretical correctness does not always translate into real world gains. So here we have a worked out example that is Viterbi decoding step by step, which I'll walk you through. Let us make this concrete with a worked out example over here. Our sentence is time flies. And we have three possible tags: NN for noun, verb for third person, VBZ for third person singular present verb, and VBP for base form present verb. Let's come to step one. We look up the emission probabilities. These are the K values. How likely is each word given each tag? We see that flies has a notably higher emission probability under VBZ, that is 0.010, and then under NN we have 0.001. That is a meaningful signal, right? Then come to step 2. We look at transition probabilities. These are the H values given the previous tag. How likely is each next tag? Starting from the start state, NN has probability 0.25. Words at the beginning of sentence are often nouns. VBZ has only 0.05. Starting a sentence with a verb is less common, right? But notice that after NN, transitioning to VBZ has a strong probability of 0.3. Right, so next come to step 3. We fill the Viterbi lattice. For the word time, the score for each tag is just the transition from start multiplied by the emission. NN gets 0.25 times 0.001, which equals 2.5 times 10 to the minus 4. This is the highest for time. Now for flies, we take the best incoming score, the NN score of which is 2.5 e to the power minus 4, and multiply it by the NN to VBZ transition of 0.3 and the emission of flies given VBZ of 0.01. This gives 7.5 times 10 to the minus 7, marked with a star because it is the highest score in that column. Best path is time tagged as NN, flies tagged as VBZ with a final score of 7.5 e to the power minus 7. The Viterbi algorithm has found this path without enumerating every possible combination. The tri-class HMM model. This is the crux of this paper. Now we need to specify the actual mathematical model. What does P, W, T look like concretely? That is what this section answers. The tri-class HMM model, two independence assumptions. The exact joint probability of a sentence and its tags involves for each position a probability that depends on the entire history of everything that came before. Written out in full as shown at the top of the slide, it is completely intractable. The number of possible histories grow exponentially with sentence length. We cannot estimate it from any finite corpus. So Marialdo's model makes two simplifying independence assumptions that reduces this to something manageable. Assumption 1, tag transition. The probability of tag I depending only on the probability of tag I depends only on the two tags immediately before it, not on the full history. This gives us the h function, h of ti given t I minus 2 and t I minus 1. This is called a second order Markov assumption. We only look back two steps. Why 2 and not 1? Because back one tag back misses too much grammatical context. And then you may ask why not 3? Because the number of parameters grows as n to the power t cubed. And with 3 tags back it grows as n to the power t to the fourth, quickly becoming too large to estimate reliably. Then we come to the next assumption, which is word emission. The probability of word wi depends only on its own tag ti, not on any other context. This gives us the k function, k of wi given ti. This is the emission probability given that this position has a tag nn. How likely it is to be the word cat versus dog versus bank. Putting these two together, the full triclass model is P bracket w comma t equals the product over all positions of k of wi given ti times h of ti given ti minus 2 and ti minus 1. This is the triclass model and known as the HK model, as it is a hidden Markov model. So one important practical trick over here is the dictionary constraint. If we know from a dictionary that tag t is simply not a valid tag for word w, we set k of w given t to 0 outright. This eliminates erroneous numbers of linguistically impossible alignments and makes inference much cleaner. So here is the HMM architecture with a visual diagram. This slide shows you the structure of model visually. The key insight is in two layers. The top layer shown as ovals contains the tags T1, T2, T3 tagged here as DT, NN, VBD. These are the hidden states. When you look at raw text, you do not see the tags. They are hidden. The arrows between tag states represent the H transition probabilities. Each tag depends on the two preceding tags only. Now let's look at the bottom layer, shown as rectangles, contains the word the cat sat. They are observed. You can see them. The downward arrows from each tag to this word represents k emission probabilities. This is the fundamental HMM structure, a chain of hidden states generating a sequence of observations. The hidden in Markov model, basically in the hidden Markov model refers specifically to the fact that tags, that is the states, are not observed in the data. Our job during training is to infer them, and during decoding to find the most likely assignment. So here we have the Python implementation of the triclass HMM. This slide shows the direct Python implementation of the model we just described. The class triclass HMM has two data structures. Self.h is a nested dictionary where h of t1, t2, t3 gives the probability of tag t3 given the preceding tags t1 and t2. Self.k is a dictionary where k tag word gives the emission probability of the word from that tag. The probability method implements the formula we just derived. It iterates over each position in the sentence. For each word tag pair, it looks up the two preceding tags, defaulting to a start symbol at the beginning of the sentence, multiplies in the transition probability h, and then multiplies in the emission probability k. The product over all positions gives p of w comma t. Notice how closely this mirrors the math. There is a direct correspondence between the equation on the previous slide and the code here. That is by design. And it is a good habit to always check that your code matches our equations term by term.
We have the model. Now, how do we actually estimate those h and k values? This is where the paper does its main work, and where the most important results come from. The first training approach is conceptually the simplest imaginable. If you have hand-tagged text, that is a corpus where every word already has its correct tag, you just count things. For the transition probability h, you count how many times the trigram t1, t2, t3 appears in your tagged corpus, and divide by how many times the bigram t1, t2 appears. That ratio is your estimate. For the emission probability k, you count how many times word w appears with tag t, and divide by the total count of tag t. Simple, clean, and it works well, as long as you have enough data. The problem is what happens to any tag trigram you never saw in training. Its count is 0, so its estimated probability is 0, and a 0 probability is catastrophic. If even one trigram in a test sentence gets probability 0, the entire sentence alignment gets probability 0. The model completely breaks down on that sentence. The fix is interpolation smoothing. Instead of using the raw RF estimate directly, you blend it with a uniform distribution, one that assigns equal probability to every possible tag. The blending coefficient, lambda, controls the mix. When lambda is 1, you fully trust your counts. When lambda is 0, you fall back to pure guessing. The key is that lambda is tuned automatically on held-out data, and it rises as training data grows, because more data means more reliable counts. Let us make smoothing concrete with actual numbers. Suppose we want to estimate h of nn given dt, jj. That is, the probability of a noun following a determiner and an adjective, like the big cat. We'll look in our small corpus and find that the trigram dt, jj, nn appeared 3 times, while the bigram dt, jj appeared 10 times. Our RF estimate is therefore 3 divided by 10 equals 0.30. Now, our uniform fallback is 1 divided by nt, with 76 tags in this paper. That is 1 over 76, approximately 0.0132. We are working with a model that was trained on 2,000 sentences, which the paper found gives a lambda of 0.77. So our smoothed estimate is 0.77 times 0.30 plus 0.23 times 0.0132. That comes out to 0.231 plus 0.003, giving 0.234. Notice what happened. The raw count gave 0.30, but after smoothing, our estimate is 0.234. We pulled it slightly toward the uniform distribution, which reduces our confidence in the specific count while ensuring it never reaches 0. The insight at the bottom of the slide is critical. Lambda grows with data. With only 100 training sentences, lambda is 0.48. We distrust our counts and rely heavily on the uniform fallback. With all 40,000 sentences, lambda rises to 0.94. We trust our counts almost completely. This is the right behavior. As data grows, the RF estimates become more reliable and deserve more weight. This slide shows the RF training algorithm in Python. The function rftrain takes a tagged corpus that is a list of sentences where each sentence is a list of word tag pairs. It maintains 4 counters: trigram counts of tag sequences, bigram counts, word tag counts, and tag counts. For each sentence, it prepends 2 start symbols to handle the beginning of sentence case, and then walks through each word tag pair, incrementing all 4 counters. After processing the full corpus, it computes the relative frequencies in one pass each. H is built from trigram counts divided by bigram counts, and K is built from word tag counts divided by tag counts. The output is 2 dictionaries, H and K, that directly plug into the tri-class HMM class we saw 2 slides ago. Notice that no smoothing is applied here. In a full implementation, you would add the deleted interpolation step on top of this, but the counting logic itself is exactly what you see. Now we come to the second training approach, that is the Baum-Welch algorithm. And this is the one that generates the paper's most interesting results. What if you do not have any tagged text at all? What if you only have raw word sequences, just the words with no labels? This is actually a very realistic scenario, because labeling data is expensive and slow. Raw text, on the other hand, is everywhere. The Baum-Welch algorithm, also known as the forward-backward algorithm, and an instance of the broader EM framework, handles exactly this situation. It iterates between 2 steps. The E step, or expectation step. This is where, given the current model parameters for every sentence in your training data, we compute a probability distribution over which tag was most likely assigned to each word. You do not get hard labels, you get soft fractional probabilities. Think of it as the model saying, I'm 70% confident this word is a noun, 20% it's a verb, 10% something else. The M step, or maximization step. In this, Take those soft probabilities and use them exactly as you would use hard counts in RF training, but instead of integer counts, you use fractional expected counts. Re-estimate h and k from these fractional counts. This produces a new model. Repeat. At every iteration, the likelihood of the training word sequences is mathematically guaranteed to be non-decreasing. The algorithm always improves, or at worst, stays the same on its training objective. But here is the warning. Notice it is highlighted on the slide. Likelihood is not the same as tagging accuracy. The algorithm optimizes one thing. We care about another. This distinction is the entire point of the paper, and we will see it play out dramatically in the experimental results. Let us look at the forward-backward algorithm. That is, exactly how the E-step computes those soft tag probabilities. For each position I in a sentence and each possible tag T, we need to know what is the probability that position I was tagged as T given the full word sequence. To compute this, we define two quantities. The forward probability alpha of I and T is the probability of having emitted words W1 through WI and being in tag state T at position I. It is computed left to right, starting from the beginning of the sentence and working forward. Each alpha depends on the previous alphas, the transition probability, and the emission probability. The backward probability beta of I and T is the probability of emitting words WI plus 1 through WN, given that we are in state T at position I. It is computed right to left, starting from the end of the sentence and working backward. Multiplying them together and normalizing gives the posterior. That is the probability of Ti equals T given W. This is the soft assignment, the probability that word I has tag T, considering all possible ways the rest of the sentence could be tagged, both before and after position I. In the M step, these posteriors become the fractional counts. To re-estimate K, W given T, you sum the posterior probability of tag T at every position where the word is W, across all training sentences, and normalize. Both forward and backward passes run in order n times nt squared, efficient enough for practical use. This slide translates the Baum-Welch algorithm, that is the forward-backward mathematics, directly into code. The forward function initializes the first row of the alpha matrix using the start to tag transition and the emission probability of the first word. It then fills the matrix row by row, left to right. At each position I and tag j, it sums over all possible previous tags j2, the product of the previous alpha value, the transition probability, and the emission probability. The backward function initializes the last row to all ones. From the end of the sentence, the backward probability is 1, regardless of tag. It then fills the matrix right to left with each beta depending on the transition to the next tag, the emission of the next word, and the next beta value. To complete one EM iteration, you would compute alpha and beta for every training sentence, and then compute the posterior as alpha times beta normalized. Accumulate fractional counts into new H and K estimators, and finally normalize to get the new model. The comment at the bottom of the code reminds you of that final step. This is the engine that Merialdo used for the unsupervised training experiments. Now let us see what happened when he ran it. We have the model. We have two training strategies, and we have a large dataset. Now let us look at what the experiments actually found. The dataset used in this paper is the Lancaster IBM tree bank. 42,186 sentences, approximately 1 million words, drawn from Associated Press Newswire. These sentences were manually tagged by human annotators, which makes this a gold standard labeled corpus. The original 159 tag scheme was reduced to 76 tags for these experiments. The data was split into 40,000 training sentences and 2,000 test sentences, about 45,583 test words. All accuracy figures in the paper are measured on this fixed test set. One important design decision was that the dictionary used to constrain the model was built from the training corpus itself. Every word's valid tags were determined purely by the tags that word actually received somewhere in training. This is tighter than a general dictionary, and it acts as a strong constraint that rules out many implausible alignments. The bottom of the slide addresses a question you might have. Why is the zero training baseline 77%, not 50% or lower? The answer is that roughly 48% of words in this corpus have exactly one valid tag. There's no ambiguity at all for those words. So a tagger is always right about them, regardless. Another 25% of words have only two valid tags, so even random guessing gets half of those right. Together, these highly constrained words push the baseline to 77% without the model having learned anything meaningful. Keep this in mind when interpreting the accuracy numbers. The interesting range is really between 77% and 100%, not 0% and 100%. Here are the results for RF training, indicating that more labeled data always helps. Look at the table carefully. Every row adds more labeled training data, and the pattern is clean and consistent. Starting at 77% with zero training data, accuracy jumps to 90% with just 100 labeled sentences. This is a gain of 13 percentage points from barely more than 100 examples. With 2,000 sentences, we reach 95.4%, already a very low error rate. At 5,000 sentences, 96.2%. At 10,000, 96.6%. At 20,000, 96.9%. And using all 40,000 training sentences, we reach 97%. But notice the third column, improvement versus previous. The jumps get smaller and smaller. The first 100 sentences contribute 13 percentage points, going from 10,000 to 20,000 sentences. 10 times as many additional examples contributes only 0.3 percentage points. And going from 20,000 to all 40,000 contributes just 0.1 percentage point. This is the classic pattern of diminishing returns in machine learning. The early data does the heavy lifting. Later data barely moves the needle. The interpolation coefficient lambda tells the same story. It rises steadily from 0 to 0.94 as the RF estimates become more trustworthy. The practical implication is, if you are building a POS tagger today and you have a limited annotation budget, spend it getting a few thousand high-quality labeled sentences. That will get you most of the way to peak performance. This accuracy versus training set size chart shows the same data visually. The curve starts at 77%, rises steeply through the first few data points, and then flattens dramatically as it approaches 97%. The three call-out boxes on the right capture the key milestones. With no training data at all, pure uniform distribution, we are at 77%. With just 100 labeled sentences, we jump to 90%. And with all 40,000 sentences, we reach 97%. The takeaway at the bottom is worth saying clearly. The first 2,000 sentences eliminate roughly 80% of all the errors that the full dataset eliminates. Everything after that is diminishing returns. The curve shape here is not specific to POS tagging. You see it in virtually every supervised learning setting. The first data points are the most valuable. Now let us look at the surprise element of the Baum-Welch training. This is the finding that made this paper famous. Look at this chart very carefully. There are 4 lines, each corresponding to a different starting point. An RF model trained on 100 sentences, 2,000 sentences, 5,000 sentences, or all 40,000 sentences. The x-axis shows Baum-Welch iterations 0 through 10, and y-axis is tagging accuracy. Look at the blue line, starting from 100 labeled sentences. It begins at 90%, rises through the first 3 iterations to a peak of about 93.1%, and then slowly declines. So for a weak starting model, Baum-Welch genuinely helps. This is reassuring. The algorithm does what it is supposed to do when there is room for improvement. Now look at the red line, starting from all 40,000 labeled sentences at 97%. What happens after the first iteration of Baum-Welch? It drops to 96.8%. After 2 iterations, 96.4%. After 10 iterations, 95.2%. The model has fallen nearly 2 full percentage points. That represents roughly 800 additional errors on the test set. And the orange and green lines, starting from 2,000 and 5,000 sentences respectively, show the same pattern. They might benefit from one iteration, but then they degrade continuously. The call-out on the right makes the critical point explicit: perplexity. The model's likelihood of the training word sequences keeps falling through all of this. The algorithm is doing exactly what it is mathematically guaranteed to do, improving likelihood at every step. Yet accuracy falls. Likelihood and accuracy are moving in opposite directions. This is the paper's central, counterintuitive finding. So, why does ML training hurt a good RF model? This slide gives 4 interlocking explanations for what we just saw. Let me take each one in turn. Reason 1 is that perplexity is not accuracy. Baum-Welch maximizes the likelihood of word sequences, but we evaluate the model on tagging accuracy, that is correctly labeling each word. These are related objectives, but they are not the same. A model can reshuffle probability mass in ways that make word sequences more predictable without making tag assignments more accurate. Reason 2 is the probability mass redistribution. Baum-Welch adjusts emission probabilities so that each tag better predicts its words, but the optimal redistribution for word prediction may not match the linguistically correct tag assignments. The model learns to be a better text predictor. That is its objective, not a better grammar annotator. Reason 3 is that the RF starting point is already good. When you have trained a 40,000 labeled sentences, your RF estimates are highly reliable. Baum-Welch has essentially nowhere useful to go. Any change it makes is more likely to disturb a well-calibrated set of parameters than to improve them. It is solving a problem that does not exist. Reason 4 is that text is not speech. The Baum-Welch algorithm was originally developed for speech recognition, where the relationship between acoustic signals and phonemes is continuous, noisy, and genuinely uncertain. There is a lot of rich hidden structure for EM to discover in speech data. In text, word tag relationships are largely deterministic. The word the is a determiner more than 99% of the time. There is not much hidden structure left to discover. When Baum-Welch tries to find it anyway, it introduces noise rather than signal. Given that unconstrained Baum-Welch hurts good models, Marialdo explored whether imposing constraints could prevent the damage. The first constraint is called the TW constraint. The idea is simple. For the 1,000 most frequent words in the vocabulary, fix their emission probabilities and do not let Baum-Welch change them. The rationale is that frequent words have so many training examples that their RF estimates are already highly reliable. Lock them in and only allow the algorithm to adjust the less well-estimated parameters. The result? After 10 iterations, accuracy under TW constrained training is 96.09% compared to 95.21% with unconstrained training. The constraint meaningfully slows the degradation, as you can see in the table, but it does not stop it entirely. The second constraint is called the T constraint. This one keeps the marginal tag distribution, the overall frequency of each tag across the corpus, constant throughout the training. It is harder to implement because PT is not a direct parameter of the model. It is derived from H and K together. Marialdo applied this to a simplified biclass model rather than the full triclass model. The result is the same story. Degradation is slowed but not prevented. The lesson from both constraints is that they attack the symptom rather than the cause. The fundamental problem is the objective mismatch. Likelihood and accuracy point in different directions, and no constraint fully resolves that. Given everything we have seen, what should you actually do in practice? Marialdo ends the paper with a clear 5-step recommendation, that is, a hybrid approach. Step 1. Get as much hand-tagged text as you can afford. As the RF results showed, every labeled sentence helps, especially the early ones. Step 2. Train an RF model on all of it, with interpolation smoothing. Tune your lambda on a held-out development set. This is your baseline and may already be your best model. Step 3. Collect raw, unlabeled text. This is cheap and abundant. There is no shortage of it. Step 4. Run Baum-Welch iterations, but cautiously. At each iteration, evaluate tagging accuracy on your development set. Do not just blindly run the algorithm to convergence. Step 5. Stop as soon as accuracy stops improving. Use the model at the iteration with the best development set performance. That is your final model. Do not keep running. This early stopping criterion is the key insight. Today, We use exactly the same principle when training neural networks. Monitor validation loss or validation accuracy and stop when it stops improving. Mary Alder was recommending this practice in 1994 in the context of HMMs, and it remains one of the most reliable pieces of practical advice in machine learning. Now, let us look at the takeaways and modern context. Let us pull back and think about what this paper means, both as a piece of 1994 work and as a source of lessons that are still relevant today. There are 6 key takeaways from the paper, and I want to go through each one because they are all worth committing to memory. First is that labeled data is gold. More hand-tagged text consistently yields better accuracy with strongly diminishing returns beyond a few thousand sentences. But the first few thousand are extraordinarily valuable. If you are ever deciding where to invest effort in building an NLP system, supervised data almost always has the highest return. Second is that ML training can hurt. Applying Baum-Welch on top of a good supervised model degrades accuracy even as perplexity improves. This is not a quirk. It is a fundamental consequence of optimizing a proxy objective. Third is that perplexity is not accuracy. The objective you optimize during training is not the same as the metric you care about at evaluation time. This gap between the training criterion and the evaluation criterion is one of the deepest practical challenges in machine learning. Always evaluate the metric you actually care about. Fourth is that Bitterby approximately equals ML decoding. The theoretically correct decoding criterion for per-word accuracy differs from Viterbi, but in practice they are nearly identical. Theoretical optimality does not always pay off. Fifth is that constraints slow degradation. Locking reliable estimates during EM helps, but does not fully solve the objective mismatch problem. They are a band-aid, not a cure. Sixth is that a development set must be used. Early stopping based on held-out accuracy is the correct and practical way to use Baum-Welch in this setting. This generalizes to virtually every iterative training algorithm. Now let us look at the lessons learned from 1994 HMM to 2024 transformers. This comparison table is worth sitting with for a moment. The surface has changed dramatically in 30 years, from a second-order HMM to a fine-tuned transformer, but the underlying principles have not. POS accuracy has moved from about 97% to over 98.5% on standard benchmarks. That is a genuine improvement, though perhaps smaller than you might expect given the revolution in model architecture. The key supervision story is unchanged. Both systems rely fundamentally on hand-annotated corpora. The tree bank is still at the heart of state-of-the-art taggers. Most strikingly, look at the core lesson row. In 1994, the lesson was that optimizing likelihood does not equal optimizing accuracy. In 2024, the same lesson appears in a different guise. Reinforcement learning from human feedback, or RLHF, trains language models to maximize a reward signal. But that reward signal is an imperfect proxy for what we actually want: helpful, honest, harmless behavior. When models learn to maximize the reward without satisfying the underlying goal, we call it reward hacking. It is exactly the same phenomenon Mary Alder documented in 1994, just at a vastly larger scale. And evaluation? Dev set early stopping, unchanged. And that brings us to the end. The full reference is Mary Alder B., 1994, Tagging English Text with a Probabilistic Model. Computational Linguistics, Volume 20, Number 2, pages 155 to 171. The topics we covered today include POS tagging, hidden Markov models, Bitterby decoding, relative frequency training, interpolation smoothing, and the Baum-Welch algorithm. This forms a foundation that runs through decades of NLP research. Even if you never work with HMMs directly, the core lessons about objective mismatch, the value of labeled data, and the importance of evaluating the right metric will serve you throughout your career. Thank you.
Hello everyone, and thank you so much for joining us today. Welcome to our paper presentation for natural language understanding. Today, we have the privilege of unpacking this truly foundational paper in modern artificial intelligence. We will be discussing the ground-breaking paper, Attention is All You Need, authored by Ashish Vashwani. This monumental work was published in NIPS in 2017. This presentation is brought to you by me, Abhinab Bezbaruah, Deepraj Majumdar, and Prashant Kumar. We'd also like to extend our deepest gratitude to our course instructor, Dr. Anand Mishra, and his teaching assistant, Ravi Saxena, Rishi Chabra, and Meenal Joshi, for their guidance here at IIT Jodhpur. So before we dive in, let's look at what our roadmap for today's discussion will be. We'll begin with an introduction and background to set the stage. What is neural machine translation and where were we before this paper? Next, we'll explicitly define the problem, specifically what we call the information bottleneck. Then we'll introduce the big idea, the soft attention mechanism. From here, we will break the architecture step by step. We will look at the bidirectional encoder, dissect the mathematical mechanics of the attention mechanism, and explore how the decoder utilizes this new concept. Finally, we'll walk through the fascinating real world example of translating English to French, allowing us to see the model's brain in real time. Let's get started. Let's start at the beginning. What exactly is machine translation or MT? At the core, MT is the task of automatically converting text from one language to another. For example, taking an English sentence and converting it to French. Within its field, machine translation or NMT tackles this challenge by using deep learning models that are pre-trained on massive parallel corpora, essentially a giant dataset of translated sentence pairs. To appreciate why this paper matters, we have to look back. Before 2014, the industry standard was phrase-based statistical models like Moses. These systems were incredibly complex to build. They required engineers to handcraft features and build entirely separate alignment models. Then neural machine translation changed everything. Suddenly, a single end-to-end neural model could learn to translate directly from raw data. However, the standard sequence-to-sequence models of the era still had a fatal flaw. An encoder RNN would read the source sentence word by word and produce a single fixed size vector to summarize the entire input. The decoder RNN would then read the single fixed vector and try to generate the target sentence one word at a time. This worked perfectly for short, simple sentences, but for longer ones it failed dramatically because the fixed vector was simply too small to hold all the necessary information. This paper solves the exact limitation by introducing dynamic position specific context vectors, the concept of soft attention, which directly inspired from the modern LLMs we use today like ChatGPT and Claude. The problem. So what exactly does the standard encoder-decoder architecture fail so badly on long sentences? It all comes down to the information bottleneck. Imagine trying to memorize a 50-word paragraph and then someone forces you to summarize all its nuances, grammar, and vocabulary into a single rigid thought before you are allowed to speak. That is what standard model was doing. The fixed length vector, the entire source sentence, whether it's 5 words or 50 words long, is compressed into one fixed size vector. There is absolutely no flexibility to store information for longer and more complex sentences. Information loss. Because of an RNN reads sequentially, early words in a long sentence gets progressively overwritten as the encoder reads the later words. By the time it finishes the sentences, much of the early context has been forgotten. No flexibility in decoding. Every single decoder step uses the exact same context vector to generate the word, regardless which part of the source sentence is actually relevant at that moment. As a side note, this is like reading just the last page of the book to summarize the whole story. Because of this, if you look at the performance data, the blue scores, our metric for translation quality, falls sharply when the sentence exceeds 30 words. The model simply runs out of memory. The big idea. Faced with this bottleneck, the researchers introduced a massive paradigm shift, the soft attention mechanism. The key insight is brilliant yet highly intuitive. Instead of forcing the model to compress the whole sentence into one vector, which why not let the decoder look at different focus parts of the source sentence at each decoding step. Let's use the human translation analogy to visualize this. When a human translates the phrase European Economic Area into French, they do not read the whole sentence, memorize it, and close their eyes and write them from memory instead. Instead, they glance back and forth. They look at the word area specifically when writing the French word zone. They look at economic when they write economic. This paper teaches the neural networks to do exactly the same thing. Run a bidirectional RNN over the source sentence so every word captures context from both the left and the right. At each step of decoding, compute and relevance score between the current decoder state and each every single source word. Highly relevant positions get higher scores. Apply a softmax function to turn these scores into percentages or weights that sum to 1. The model then computes a dynamic context vector, which is a weighted average of all source annotations and uses that specific vector to generate the next word. Ar- um, let's look under the hood and see how this is built, starting from the architecture part, the bidirectional encoder. Why do we need it to be bidirectional? Well, a standard unidirectional RNN reads text the way we do, left to right, but that means it processes the third word. It has no idea what the fourth and fifth and the sixth word are. Early words lack future context. In language, what comes after a word is often just as important as what comes before it. To solve this, a bidirectional RNN runs two passes simultaneously, one forward pass going left to right and the other one backward pass going from right to left. If you look at the diagram, you can see how the final annotation for each word represented by H is actually a concatenation of both the forward and the backward passes. Now, every single word essentially contains a snapshot of the full sentence context, heavily emphasizing its immediate surrounding words. Because this representation is so much richer, the attention scores we compute later become vastly more meaningful. The decoder can truly understand the nuanced context of each source position represents. Moving on to part 2, we arrive at the core, the attention mechanism itself. This is how the decoder decides which source words to focus on. For each source position, the model computes an alignment score. Using a small learned neural network, mathematically it asks the model, given what I just translated, how much should I focus on this specific source word right now? Raw scores are not very useful, so we normalize them. By applying a softmax function, these scores are turned into probabilities, numbers between 0 and 1 that sum up to 1. These are our attention weights. Step 3, the model then computes the new dynamic context vector. It calculates the weighted average of all the source annotations. For example, if the attention weight for word 3 is 0.8, then the word 3 contributes 80% to the context vector. The decoder is essentially looking for mostly for word 3 for the specific step. Step 4, finally the decoder uses the tailored context vector combined with his previous state and the last output word to generate the next word in the target language. Now let's understand the mathematics. To really appreciate the elegance of this, let's step through the mathematics of the attention formula. If we are familiar with the modern transformers, we will recognize query key value architecture. First, we compute similarity scores. We multiply each query vector, which represents what the model is looking for, with all key value vectors, which represent what the source words contain. A high dot product scores here means, hey, this is what the source word is highly relevant right now. Second, we scale down the scores. We divide the results by the square root of the key dimension. Why? Without this scaling, the dot products can go extremely large. If we feed massive numbers to a softmax function, it pushes the gradients to near zero, which stops the network from learning entirely. This scaling keeps the math stable. Firstly, third, we apply softmax to convert those scaled scores into clean percentages weights. It tells the model, for example, to pay 60% attention to position 1 and 10% to position 2. Finally, we compute the weighted sum of values. We multiply each value vector by its assigned weight and add them together. The result is a beautifully blended representation that emphasizes only on the most relevant scored words. Now we'll tie it all together in architecture, the decoder. At each individual decoding step, the decoder receives the previously generated word. It computes attention over all source annotations to get the brand new context vector. It updates its hidden state and it predicts the next word. If we look at the comparison table, The difference is so stark. In standard sequence to sequence models, the exact same context vector is used at every step, causing long sentence to degrade badly and requires separate training steps for alignment. But in the attention models, a new context vector is computed at every single step. It creates soft, learned alignments on the fly. Its performance stays strong even past 30 words. This is incredibly important. This entire system is trained jointly end to end. The encoder, the attention network, the decoder all learn together by maximizing the probabilities of generating the correct translation. Now that we understand the maths and the architecture behind these dynamic context vectors, I'm going to hand the presentation over to Prashant. He will walk us through the exactly what this looks like in action during a real translation and cover the performance results. Prashant?
Thank you so much. Now I would like to share my screen. I hope my screen is visible.
Yes.
Okay, thank you so much. So now let's see this in action with a worked example. Imagine translating European Economic Area into France. France put describing word after noun. The model smartly print the French word zone for area first, and then doing this, it put 75% of its focus at the very end of the English sentence on the word area. Then to translate economic, it jumped backward to focus on economic. Nobody taught it French rules. It learned how to mix up the word order just by learning where to look at. Moving on to the next slide. So here we see alignment heat map visualization. We see the learning on color map. English word are on the bottom, French word are on the left. Notice the strong line right down the middle because English and French are somewhat alike. The first word often match the first word, but look outside the middle line. When English phrase was signed, becomes three word in French. The model naturally spread its focus across the middle multiple words. It handled messy translation easily. So now we look at the transformer architecture. So Badhanau's idea was great, but it still used older network that read slowly, one word at a time. The 2017 Transformer paper asked a bold question: what if we drop those slow network RNN and only use attention? Instead of reading word by word, the transformer look at the whole sentence at once. Every word looks at every other word at the exact same time. This means we can train these models superly fast because they do everything at once. Next, scalar dot product attention. This is the heart of the transformer. Is Think of a library. You bring a query like book on space. The computer has a key, the title of all the book. You match your query to the quick keys. Once you find the match, you pull the actual book, the values of the self. The transformer does this with math. It match word to find the exact meaning it need to find in a split second. Multi-head attention. Because language is tricky, searching just once might miss things. So the transformer search 8 times at once. This lead to the model where different heads. One search might look for grammar links, another search might figure out the word it refers to the law. By looking at the sentence in many different way at the same time,
a really deep understanding of the text. Badhanu Attention versus Transformer. Let's compare these two big ideas. Badhanu gave us the idea to let the model look around dynamically, but it was slow and only looked in one way at a time. The transformer made this much strong. It made everything super fast and looked in many way at once. While Badhanu scores were good, the transformer beat all previous record by a miles, as you can see here. Experimental setup. To see how good this is, let's look at the text test. The model translates a huge pile of text, nearly 350 million words. Quality is measured by blue score. This just check how closely the computer works, match a real human translator. The scale goes to 100 and anything over 30 is considered as good translation. Results. Blue score comparison. The results were amazing. The old model that didn't use attention score scored a low 17.8 on long sentence. Adding Badhanu Attention bumped the score way up to 26.75. When finally trained, it hit 36.15. It did the absolute best older system in the world, even though the older system used 40 million extra words to train. The new design was totally win. Robustness to sentence length. But the most important result is this graph. The red and yellow line are the old model. Notice how they drop off a cliff when a sentence gets longer than 20 words. Just forget what they read. The green line is the attention model. It stays completely flat and strong, even for 60 word sentence, because it can always look back, it never forget. Finally, why soft attention is better than older hard rules. Hard rule force a strict choice. One English word must match exactly one French word, but language doesn't work like that. Soft match, soft attention use flexible percentage, easily handle phrases where two words become one. Best of all, smooth percentage make the math easy for the computer. It can learn from its mistake in one smooth flowing step. Now I would like to hand over the rest of the slide to Deepraj. Thank you.
Thank you, Prashant. That was a nice move. Anyways, I would like to take on the rest of the presentation from now onwards, and I would like to give you all a beautiful demonstration of the rest of the paper. So just let me share my screen and start presenting it. Okay. So So the, this is the PyTorch implementation of the Badhanu Attention, okay, as well as the how this transformer works, okay. So a minimal working implementation has been made, so we get the encoder, okay, that is the forward as well as the backward stuff, okay. So in the encoder we are initializing first the embeddings having the size of vocabulary and embedding size that we pass as the initializing constructor. Then we have the bidirectional RNN, and apart from that we also do a forward pass, okay, and there we pass on the batch size and source length and the rest of the other things. And there's also this attention where we use, that is the Badhanu Attention, having two like UA and VA, having the linear layers and the respective passed on hidden dimension, encoded hidden dimension, and again the hidden dimension. And then we have this forward pass, okay, where we have the self WA, self WE, there we take it as SE, and alpha as F dot max, and C as alpha into H, all with the summation of 1, okay. So we'll be going through a quick demonstration, okay, of the given paper through the demo using a collab file that I've already created. So just allow me to share that script with all of you. So this is the transform implementation of the paper attention is all you need. Okay, so here what we do is like we go through a multi-head retention, then the script is totally based upon the trained, I mean, first we define the model, then we go through a training phase, and then we go through the different embeddings like the positional embeddings, the training loop and the casual masking, and then we go for the result and performance. So first, like we are looking at the attention is all you need architecture. Unlike older models that only read word by word, the transformer looks like an entire sentence at once using the attention. So first is the, we can see over here the multi-head attention class. Okay, so here what we do is like, is the core one. So I mean the multi-head attention class is the core one. It uses queries, keys and values to decide which word in a sequence are most important to each other. And also, like, by having multiple heads, as we can see in the code, the model can focus on different aspects of data simultaneously, like grammar and meaning and whatsoever. And after that, we also see over here the positional embedding encodings. Okay, so in positional encoding, what we do is like, since transformer don't process data in order, so they don't naturally know where a word sits in that particular sentence, right? So in that particular sentence, what we do is like we do positional encoding, adding mathematical signals, sine, cosine waves to the input, so model understands the specific position of every token. And apart from that, what we do is like, we go through this rest of the other stuff where we define the transformer class using all these above defined multi-head attention class and all those mechanism, with also like class feed forwarding and also like class positional encoding. And then we ultimately call all those class over here using their self declaration over here, and we create the ultimate transformer object. And after that, we just generally go through the training loop and causal masking, where like we train the model to reverse sequences. Like we used a causal mask in the decoder. This is crucial. What I think is like it acts like a blindfold, right? It acts like a blindfold, and that prevents the model from cheating by looking at the answer, I mean the future tokens, during training. So that is the overall analogy what the paper meant to say, and what we also try to implement over here. So we just simply, took a vocab size of 24 just for the demo purpose. If you want to do more, you can just increase the vocab size, define your own data set, and then, run the sequence length and all those things. So we ran it for like epoch of 116. We can see like it has gradual meaning, right? Like over the uh, you know uh, I mean, to some extent it increased, but okay, no problem, since our data set is very small and not that big, and also like we're doing it on a very trivial, like very trivial task. So we can see like the loss is like decreasing over time with per like epoch as we keep on increasing. And then at the end we can also see like the model, the model started with high error but converged quickly. So also in the end we achieved something like 99% accuracy. So this proves that transformer is incredibly efficient at learning complex sequence mapping even with small amount of data. So that was the overall kind of implementation that we try to do it for over from here. So let me get back to the slides and stop this demo. So what we'll be doing over here is that, like, going back to our old presentation slides for understanding the thing much better. So I hope my screen is visible. So what we did is like we implemented that thing, and now what is the like what was the legacy impact from Badhanu attention to transform attention is all you need, and then to modern AI. The first thing is that Badhanu et al. It came into 2014, and first differential softmax attention for soft attention for NMT and attention weights, like bidirectional encoder, how they worked, how they jointly trained end to end on, and it also achieved like 20,000 plus citations. Then we got long attention. It's like kind of simplified version of the. Like it is not introducing unnecessary complexity like Badhanu Baidhanu's work. So there it just goes on and it does some kind of multiplicative scoring, which is even faster, and it has global and local variants, so widely adopted in subsequent NMT systems. Apart from that, after we got in 2016 we got Google NMT GNMT. So it is kind of like production scale attention model deployed in Google Translate that we used to do earlier in our childhood days in go, like age old nostalgia, where we used to use Google Translate for translating languages and sending text and all those things. Then in 2017 transformer, the attention is all you need, the main paper that came, it removed RNNs entirely and started using the concept of multi-head attention at every layer, like fully parallelizer. And on a brew like a BLEU blue score, it got something like 28.4 and encoder stuff. And also like there we got direct extension of Badhanu's insight, like what Badhanu want to convey, or it kind of like the gap that he had left. Then in 2018 we got BERT and GPT-1. Like as we all do use GPT, so it was the foundational model for all those systems, like transformers that are pre-trained on massive corpus, including BERT that is bidirectional for understanding tasks, and like GPT that is only the decoder and model for auto-recursive stuff, like for generation. Both are still used today for research purposes and getting hands-on on working on NLP stuffs and all those things. So in 2022 and further, we got Claude, Gemini, Llama, and all those multimodal, which does not only work on this text, but rather on billions of parameters, including multimodal inputs on the same core, and also attending to what is relevant. Like every line of code traces back to Badhanu et al. So ultimately, if we want to thank someone, that is Badhanu, because their work somewhat inspired the and also laid the foundation of all modern LLMs and also the agents and everything. So going to the next slide, like we take the summary of what we did in our entire paper. Like since we got to see that it's a fixed length vector, and also like we got attention dynamic focus context, and also we got to see soft alignment and bidirection encoder. And also like the thing we got here is like attention is all you needs, what are the impact over there and what are the things that we need to do, and also how it fixed the attention is all you need, how it fixed this entire stuff and their implementation and how it worked. Okay, so I think that is the point. It summarizes with the fixed line vector attention, soft line alignment, bidirectional encoding, and at the end, like how this paper found the modern foundation of all the LLMs and coding agents. So I think that's it. These are the references that we use, and thank you for all your attention, questions, and discussion. We welcome them with open hearts and warm heart. And if you wanna like reach out to us, you can directly mail us or contact us. And I would at last again like to thank Dr. Anand Mishra and his respective TS, and also for giving us this platform to explain this beautiful paper and such a fantastic implementation of this work. And also I'd like to thank Abhinav and Prashant for co-working with me and co-presenting this thing for this particular presentation. So I think that's it. We'd like to end this presentation over here. Any kind of queries or any kind of stuff, we warmly welcome that thing. And I think that's it. So thank you all. Have a nice day ahead. That's it. Thank you.
Hi everyone, this is Arjun, and I, along with my teammates Mangalton and Sarita, will be presenting this paper, which is BERT, Pre-Training of Deep Bidirectional Transformers for Language Understanding, published by Jacob Devlin and colleagues at Google AI in 2019. This paper fundamentally changed how we built NLP systems, and by the end of the session, you'll understand exactly why. So let's dive in. Why BERT, the core problem? Let's start with the core problem BERT was designed to solve. Consider the word blank. If I say he went to the river bank, bank means a river bank. If I say he withdrew cash from the bank, bank means a financial institution in this case. Now, models like GPT and Elmo before BERT read text from left to right only. So when they encounter the word bank, they've only seen the words to the left. They haven't yet seen river or cash. which are the very words that disambiguate the meaning. BERT's solution is extremely simple. Read in both directions simultaneously at every single layer. So bank sees river on the left and withdrew cash on the right all at once. That's the fundamental insight. Language understanding requires both directions. The NLP landscape before BERT. To appreciate BERT, let's trace the evolution quickly. In 2013, word to wake gave us word embeddings, but they were static. The word bank always had the same vector regardless of the context. In 2019 came Elmo. It improved this with contextual embeddings using LSTMs, but it only did a shallow concatenation of left to right and right to left representations, not fully bidirectional. And in 2018, OpenAI brought in GPT, which brought transformers into the picture, but it was strictly left to right. It's great for generation, but limited for understanding. Then in 2019, BERT arrived. It's deep bidirectional transformer based, pre-trained with MLM, which is masked language modeling, and next sentence prediction, NSP. And the result was that the glue score jumped from 72.8 with GPT to 80.5, a 7.7 point improvement. That's a massive leap, right? So next, look at the building blocks. The BERT is is an encoder only architecture, right? The transformer encoder basically. Now let's look at what's under BERT's hood, the transformer encoder that is. BERT is built on stack of identical transformer encoder blocks. Let me walk you what's inside each block. Each block has essentially three components. A feed-forward neural network with hidden dimension of 3072. Think of this as the model's memory, storing factual knowledge. Layer normalization is to keep activations stable across 12 or 24 layers, and most importantly, the multi-head self-attention. The attention formula, which is also shown here, is attention QKB is equal to softmax of Q multiplied by K transpose divided by square root of dimension dk, and this whole softmax is then sort of dot product with V, the V matrix, right? So for every token, we compute three vectors: a query, a key, and a value. Think of it like a search engine. The query is what we're looking for. The keys are what every other words offers. The value are the actual content. We compute query key similarity scores scaled by square root of d to prevent the gradient saturation, then apply softmax to get attention weights, and then take a weighted sum of the values. The result is every token gets new representation enriched by information from every other token it attended to. BERT doesn't do this at once. It runs 12 attention heads in parallel, each specializing in different relationships. One head might track subject-verb agreement, another might link pronouns back to their references. Their outputs are concatenated back to 768 dimensions. This entire block repeats 12 times in BERT base and 24 times in BERT large, with each layer building increasingly abstract representations, from syntax in early layers to semantics in the later ones. Numbers to remember is that BERT base has 12 layers, hidden size is 768, 110 million parameters, and the large version has 24 layers, hidden size 1024, 340 million parameters. So how BERT treats the reads the input tokens, right? So before the transformer runs, BERT converts the raw text into vectors using three embeddings, all summed together. Look at the example, my dog is cute and he likes it, as two sentences. Token embeddings. BERT uses a word piece tokenizer with a 30,000 token vocabulary. Critically, it doesn't just split by white space, it breaks words into subword units. So uh, words like playing becomes uh, play plus hash hash ing, and unbelievable becomes un plus hash hash believe plus hash hash able. This handles rare and unseen words without an out of vocabulary problem. Each token is then mapped to a 768 dimensional vector. Next is segment embeddings. BERT frequently takes two sentences as input, a question and a passage, a premise and a hypothesis. Each token gets an additional label, EA or EB, telling BERT which sentence it belongs to. In our example, my dog is cute, and its separator gets EA. He likes it gets EB. This is what allows BERT to reason about relationship between sentences. Next is come to position embeddings. Transformers process all tokens simultaneously. So unlike RNNs, they have no built-in sense of word order. Dog bites man and man bites dog would look identical without this. BERT adds a learned positional vector E0, E1 up to E511 for each position in the sequence. Two special tokens worth noting are CLS always sits at position 0 and its final hidden state is used as a sequence level representation for classification tasks. Separator token marks the boundary between sentences. The final input to the transformer is simply the element-wise sum of all three embeddings, one 768 dimensional vector per token, encoding what the word is, which sentence it's from, and where it appears. So the first task is masked language modeling, the first pre-training task. Now we come to the first and the most important pre-training task, the masked language model or MLM. So the idea is inspired by a 1953 technique called the closed task, fill in the blank. BERT randomly masks 50% of the input tokens and trains the model to predict what those masked tokens were. But there's a clever twist in how those 15% are masked. It's not always replaced with the masked token. Instead, 80% of the time replaced with the masked token, 10% of the time replaced with completely random word, and 10% of the time it's left unchanged. So why this mix? Because during fine tuning, the mask token never appears. So if you only train with mask, the model would learn features specific to that token, causing a mismatch. The 10 to 10 trick forces the model to maintain a good contextual representation of every token, not just the masked ones. And this is what enables true bidirectionality. The next task, the second task is basically the pre-training task, which is the next sentence prediction or NSP. The motivation is clear. Many real-world tasks like question answering and natural language inference requires understanding the relationship between two sentences, not just individual words. MLM alone doesn't capture that. So BERT is trained on a binary classification task. During the pre-training, BERT is given pairs of sentences, A and B, and must predict whether B is the genuine next sentence that followed A in the original context, or a random sentence pulled from somewhere else in the corpus. So 50% of the time, B is the actual next sentence after A, labeled is next. 50% of the time, B is a randomly sampled sentence labeled not next. So look at the two examples on the slide. In the is next case, the man went to the mask store, followed by he bought a gallon mask milk. These clearly belong together. The second sentence is a natural continuation of the first. In the not next case, the man masked to the store, followed by penguin mask are flightless birds, completely unrelated. A sentence about penguins has nothing to do with the man going to a store, right? So the mechanism is, remember that the CLS token, the special classification token at the very beginning of every input. After passing through all 12 transformer layers, the CLS token's final hidden state, called the C vector, is fed into a simple binary classifier with a single dense layer and softmax. This classifier outputs is next or not next. So why does this matter for fine tuning? Based on this training objective, it forces BERT to understand discourse coherence, whether two pieces of text logically belong together. This is exactly the kind of reasoning needed for Q&A and NLI. When you later fine-tune BERT on Squad, it already has an internal sense of whether a passage is relevant to a question because it spent pre-training deciding whether sentence pairs were related. The result is that BERT achieves 97% accuracy on NSP during pre-training, showing it genuinely learns cross-sentence coherence and not just memorization.
Hello, this is Mangalton Okram, and I'm going to present the slides from here onwards. The slide here is pre-training at scale. So it shows that a word on the sheer scale of BERT's pre-training. In the paper, it is mentioned that BERT was trained on 3.3 billion words, and it combines like book corpus and also English Wikipedia. And it ranged for 1 million steps, which is approximately 40 passes over the entire corpus. And in the paper, it is mentioned that it takes 4 days on cloud TPUs, so it is really expensive, right? And for the training configuration, the base size was 256 sequences. So is up to 512 tokens. If you calculate it, then we get 128,000 tokens per batch. And the optimizer they have used was Adam with a learning rate of 1 into e to the power minus 4. So here importantly, training use sequence length 128 for 90% of steps, then 512 for the final 10%. So if you know the reason why they have done that is it is actually a computational trick to speed things up since everyone knows that attention scales quadratically with the sequence length. So this scale of pre-training is what gives BERT its power, right? And also why it launched the era of large pre-trained models. And also we can see that zero point 0.1 dropout is used on all layers, and GLU activation is actually used instead of ReLU activation function. And moving on to the next slide, pre fine-tuning. So here is what makes BERT truly remarkable. So if we have one pre-trained model, we can have many downstream tasks. So let's look at this diagram, for example. So from a single pre-trained BERT checkpoint, you can branch out to completely different tasks, but with minimal changes. For example, let's take about this text classification. So for text classification, which is like sentiment analysis, linguistic acceptability, if we take account like as an example. So you take the CLS token and pass it through a simple linear layer, right? But if we consider this question answering, for example, squat, we add like start and then end vectors to predict answer spans. And let's say if we talk about sentence pair, pair task is like until main and paraphrasing. Again, just the CLS token is used and a linear layer. And finally, if we talk about token tagging, which is mostly used in NER, that is name entity recognition, each token's representation gets its own level. And here is the kicker. So fine-tuning is cheap and it takes at most 1 hour on a single cloud TPU. So you are not training from scratch. You are just simply guiding a model that already understands language towards your specific tasks, right? As we have mentioned, different downstream tasks here. Moving to the next slide, which is hands-on running BERT with Hugging Face. So here, let's make this concrete with code. Thanks to the Hugging Face Transformers library, using BERT is remarkably simple. Right. So on the left, you can see marked LM prediction here. So just 2 lines to set up a fill marks pipeline and query it. So when you ask BERT to fill in this the man went to the and then marks. So it predicts store with 27% confidence and hospital next. So because it has seen these patterns in context during pre-training, right? So if we see to this right side, that is sentence classification, you load the tokenizer and then tokenize your input, load BERT for sequence classification, and if we run the forward pass, the logic give you class scores. And if you can see the bottom line, literally, pip install transformer stores, and you are just 2 lines away from the running BERT. Which is like saying the barrier to using this technology has never been lower, right? And moving on to the next slide. So here are the real world applications of BERT. So BERT isn't just academic, and it has shown it powers products like we use every day. For example, let's say about Google search. So Google search deployed BERT in 2019 to better understand query intent. So what it was like before BERT, a query like do aestheticians stand a lot? And it used to return like irrelevant results. But after BERT, it can understand stand means like physical standing, and it is not a concept, right? So like another example can be BioBERT, which is fine-tuned on PubMed articles and clinical notes to extract like drug interactions and diagnosis from medical records. It is even used in, say, FDA drug surveillance. And then if we talk about legal and finances, FinWork and LegalBird, they do sentiment analysis on earnings and calls and then classify contract law clauses. And it saves hundreds of billable hours. Furthermore, like multilingual bird is there, which we can also call Ambert. It was trained on 104 languages simultaneously, which can enable zero-shot cross-lingual transfer. Like if you train a sentiment model in English, and it works in Hindi without any Hindi training data, and it is if we can do fine tuning on other languages as well, right? So from the slide we can see that the risk of birth is extraordinary. And moving to the next slide, we have results after the group benchmark. So now let's look at the numbers. This table shows BERT's performance on the glue benchmark, which is a collective of diverse NLP tasks. So look at the progression here. So pre-BERT saw state-of-the-art average 74.0, and then Elmo with BiLSTM actually scored 71.0, and OpenAI GPT push it up to like 75.1. But if we see the bird base jumps to like 79.6 and then bird large reaches 82.1. So this is like a one full 7.7 point improvement over prior state of the art, which is OpenAI GPT. Right. So looking at the individual tasks, see on COLA linguistic acceptability, BERT scores 60.5 here, and versus GPT's 45.4. So this is like a 15-point gap. And if you see this QNLI, BERT large hits like 92.7 versus GPT's 87.4. So the four call-out boxes at the bottom summarizes this whole story. That is that the bird improved over prior state-of-the-art by 7.7 points on ZL glue. And then if you can see, plus 4.6 on MNLI and plus 1.5 on Squad version 1.1 and 5 plus 5.1 on Squad version 2.0. So across the board, we can see that bird base and bird large, they dominate, right? Moving on to the next slide, here's a workout example from this squad question answering. So let me walk you through exactly how BERT solves questioning and answering problem using the squad dataset. So here the question is, where was Albert Einstein born? And the passage mentions that it is born in he was born on in Ulm in the kingdom of Württemberg, right? It's the German Empire, I guess. So if we see the bird's input is CLS, the question, a separator token, the patches, and then a separator token. So during fine tuning, is vectors are learned, S for the start, and then E for N is with like 768 dimensions. So for each token in the passes, BERT computes a start score, dot product of S with that tokens representation, and it is softmax across all tokens, right? So similarly, it is the same for the N scores as well. And the base answer span is the one that maximizes the sum of the start score at position I and then the N score at position J, where J is greater than or equal to I. So here we can finally see the result in the kingdom of Württemberg is on, which is extracted correctly. So here, as we have seen in the previous slide, on Squad version 1.1, BERT Lars ensemble achieves like F1 of 93.2, which is surpassing the human F1 of 91.2. So here from this example, we can see that BERT can outperform humans at reading comprehension. So which is really amazing. So here we are at ablation studies. So it shows what really matters in BERT. So the ablation studies are where the paper gets really scientific, systematically removing components to understand what is driving its gain, like the bird's group gain, right? So here in row 1, we can see full bird base. It scores 84.4 on MNLI, 88.5 on squat, which is like the baseline to beat. Right? And in row 2, like remove NSP, QNLI drops from 88.4 to 84.9. Squad drops from 88.5 to 87.9. So NSP matters, we can see that. So especially for tasks requiring sentence peer understanding. And if we see row 3, so let's switch to left to right only. So no NSP MRPC crosses from 86.7 to 77.5 and squad from 88.5 to 77.8. So removing bidirectionality is catastrophic. This can be seen from this row 3. And from the row 4, so if we add a bi-LSTM on top of the left to right model, Squat this recovers somewhat to like 84.9, but glue text suffer. Yeah, so as we can see from this table. And here the bottom chart shows model size. As you can see that if you go from 3 layers to 24 layers, accuracy monotonically improves from like 77.9 to 86.6. So here it shows that bigger is consistently better. So even on small data sets. Now Sarita will explain from the next slides.
This comparison table between BERT, GPT, and ELMO summarizes everything we have discussed. ELMO uses a 2-layer bi-LSTM and is feature-based. It involves extraction of representations and plugging them into another model. Its bidirectionality is shallow, as it's just a concatenation of 2 separately trained models. While GPT uses a 12-layer transformer but is strictly left to right. That is, every token only attends to past tokens. It's fine-tuning based but limited in understanding. BERT, on the other hand, uses a 12 or 24-layer transformer and is deeply bidirectional. That is, every layer, every token, sees the full context in both directions. It is trained on 3.3 billion words with MLM and NSP. Now let us look at how to fine-tune the hyperparameters and what best practices must be followed while implementing BERT. The preferred batch size is of 16 or 32. The recommended learning rate is between 0.00002 and 0.00005. We must search across all three because learning rate is the most sensitive hyperparameter for fine-tuning. Epochs are preferred to be from 2 to 4, usually 3 is enough. A warm-up for 6 to 10% of steps is recommended, and a maximum sequence length of 128 is preferred if speed is the priority, while 512 is preferred for accuracy. The tips on the right are equally important. Start with BERT base uncased, as it handles most English tasks well. Watch for instability with BERT large on small datasets by running 5 random seeds and picking the best. And if you have fewer than 5,000 examples, use data augmentation, where back translation or synonym replacement can make a real difference. BERT has its limitations. Let's have a look at them here. The first limitation is that it is capped at 512 tokens, due to which long documents need chunking. It cannot generate text, as it is encoder only, so translation and summarization are out of scope. Inference is slow, at 110 million plus parameters, and interestingly, NSP was later found to be suboptimal, which Roberta removed to improve the results. But BERT's influence on what came next is enormous. Roberta trained longer with more data and dynamic masking, picking up 1 to 2 glue points. DistilBERT compressed BERT to 66 million parameters at 97% of performance, while Albert went further with parameter sharing, having just 18 million parameters. XLNet fixed the mask mismatch with permutation-based language modeling, and T5 and BART combined BERT-style encoding with GPT-style decoding for sequence-to-sequence tasks. Every modern LLM, be it GPT-4, Claude, or Gemini, traces its lineage back to the pre-training paradigm BERT established. Let us look at multi-head attention properly. Instead of one attention function, BERT runs 12 attention heads in parallel. Each head projects QKV into a lower dimensional space. That is 64 dimensions each in BERT base. Each head computes attention independently, and the results are concatenated and projected back. The formula used is multi-head output equals concatenation of all head outputs, multiplied by a learned output matrix, WO. The concrete example on the slide shows a 2-token input. After computing QKV, the scores matrix comes out as 0.88 and 0.71 after scaling. After softmax, each token attends to both tokens, with weights around 0.54 and 0.46. Neither token ignores the other. That is, both directions are captured simultaneously. Let us perform named entity recognition with BERT. The input sentence used is Jeff Bezos founded Amazon in Bellevue, Washington. BERT assigns a label to every token. Jeff gets B-per, meaning beginning of a person. Bezos gets I-per, that is inside a person entity. Amazon gets B-org, while Bellevue and Washington both get B-loc. The code is just 3 lines using Hugging Face pipelines, which involves loading the NER pipeline with BERT-based NER, passing the input sentence, and getting back structured entity predictions with confidence scores. BERT NER achieves 92.4 F1 on CoNLL 2003, a 2019 record, beating Elmo by 0.2 points. There are 5 key takeaways in this paper. Let's have a look at them one by one. Firstly, bidirectionality is crucial. Seeing both left and right context at every layer is what separates BERT from everything before it. Secondly, masked LM is the mechanism that enables bidirectionality. Masking 15% of tokens and predicting them from full context forces the model to build rich representations. The third takeaway is that one pre-trained model can perform many tasks. The same checkpoint, fine-tuned in hours, handles classification, QA, NER, and entailment, all with minimal changes. The fourth takeaway is that scale matters, but smart design matters more. BERT large helps, but the architectural choices of using MLM, NSP, and bidirectional transformer drive the main gains over GPT. Lastly, BERT is the foundation of modern NLP. Roberta, Albert, Distilbert, Deepraj, and ultimately the LLMs we interact with today all trace their lineage back to this paper. And that brings us to the end of the presentation. To summarize everything in one sentence, BERT taught machines to read the way humans do, by considering the full context of a sentence in both directions simultaneously. Thank you for your attention.